On October 21st, 2025, a shift occurred. Independent astronomical observers, correlating real-time tracking data with official NASA projections, identified an impossibility. 3 Atlas was not in its anticipated location. The displacement wasn't measured in a few kilometers, nor 1,000, but exceeded 1 million kilometers and was expanding with each passing hour. The extraterrestrial visitor, which had captured widespread attention since July, had achieved something no natural comet should be capable of. It had accelerated beyond its predicted gravitational trajectory. 8 days later, it vanished behind the Sun at the precise moment its velocity reached its zenith, concealed from every terrestrial telescope during the most energetically efficient window for any spacecraft to alter its course. Now, as it nears perihelion on October 29th, the object will remain unseen, obscured by solar glare, undertaking whatever mission brought it here in absolute darkness. Upon its reappearance in early November, we will ascertain whether the divergence was an error in our calculations or if an external entity has indeed made a deliberate maneuver. The ensuing 2 months will either affirm our observation of the most extraordinary comet in recorded history or substantiate claims that Avi's prior warnings regarding alien technology were not mere conjecture. If you share my fascination with the unfolding events in the heavens, please indicate your interest by liking this video and subscribing to ensure you don't miss future updates. I also encourage you to leave a comment specifying your listening location, the current time there, and your opinion on whether we are observing a comet or something far more purposeful. To contribute to the growth of this community, consider sharing this video and activating the notification button below. Your support is deeply appreciated. The trajectory anomaly, suggesting active maneuvering, initially emerged subtly. On October 21st, 2025, at 002 Coordinated Universal Time, a small group of independent trackers conducting routine sky surveys noted an anomaly when cross-referencing their observations with the Jet Propulsion Laboratories Horizon System. 3 Atlas, the interstellar object that had exhibited relatively predictable behavior since its discovery in July, had deviated from its course. This was not a minor deviation attributable to measurement inaccuracies or outgassing pressure. The discrepancy was significant. The object appeared ahead of where gravity alone should have positioned it. Let us clarify what this implies. When monitoring any celestial body, be it a satellite, asteroid, or comet, we are essentially observing the invisible influence of gravity guiding its path through space. The JPL Horizon System is among our most advanced astronomical instruments. It forecasts the positions of objects based on the gravitational influences of the Sun, planets, and even the subtle pull from Jupiter's mass millions of kilometers distant. These predictions are remarkably precise. During Mars rover landings, spacecraft flybys, and the tracking of near-Earth asteroids, Horizons directs our observations within margins measured in meters, not kilometers. On that October morning, Horizons' prediction indicated 3 Atlas would be located at a right ascension of 13 hours, 46 minutes, 57.51 seconds, and a declination of 8 degrees, 15 arc minutes, 20.00 arc seconds. This was the predicted celestial position according to NASA. However, the observational data presented a different scenario. Multiple independent tracking stations, cross-referencing their measurements, located the object at a right ascension of 13 hours, 47 minutes, 54.3 seconds, and a declination of 8 degrees, 21 arc minutes. For those unfamiliar with astronomical coordinates, this represents a substantial discrepancy. At 3 Atlas's travel distance, approximately 2.38 astronomical units from Earth, this angular offset translated to a lateral displacement of roughly 1.1 million kilometers. Now, here is where the situation becomes truly perplexing. When tracking systems reveal a disparity between prediction and observation, the error typically manifests in a specific direction. If your orbital data is outdated, the object appears behind its expected location. Consider it analogous to attempting to strike a moving target with outdated information. You consistently aim where it was, not where it is. Orbital mechanics follow predictable patterns. Comets accelerate as they approach the sun and decelerate as they move away. Outgassing can generate minor non-gravitational forces, small jets of vapor that subtly nudge the object off course. These phenomena are well understood and documented in thousands of comet observations spanning decades. Yet, 3 Atlas appeared ahead of its predicted position, not behind. This entirely disrupts the conventional pattern. When an object manifests ahead of gravitational predictions, it suggests an external force is propelling it forward, augmenting its motion. For a comet, this would necessitate asymmetric outgassing precisely directed to accelerate the object along its trajectory. While plausible, as comets can indeed be unpredictable, the timing of this event raises more difficult questions to dismiss. The group that first publicly documented this deviation is known as Earth Exists. They are not affiliated with NASA or any major observatory, but are part of a growing network of citizen astronomers who have independently undertaken the task of tracking 3 Atlas using publicly accessible telescope data and sky survey archives. While amateur observations might sometimes be disregarded, these are not amateur efforts. These individuals possess access to sophisticated equipment and a thorough understanding of astrometry, orbital mechanics, and photometry. They have diligently cross-checked their findings against multiple data sources, compared images from various observatories, and conducted their own calculations. According to their analysis, released on October 22nd, the positional discrepancy was not static, but was actively increasing. 19 hours after the initial October 21st observation, they performed another positional analysis, revealing that the divergence had grown. They calculated the rate of this divergence to be approximately 0.23 arc minutes, which, at that distance, equates to a lateral velocity change of nearly 4 kilometers per second. This is not mere drift or measurement noise. It represents a sustained departure from the anticipated gravitational path. To contextualize 4 kilometers per second, this is approximately 14,400 kilometers per hour. For comparison, the fastest human-made spacecraft, the Parker Solar Probe, reaches speeds of about 192 kilometers per second at perihelion. But this is a result of falling towards the sun with significant gravitational assistance. We are discussing lateral motion here, perpendicular to the primary trajectory. Such a velocity change necessitates a force. For a comet, this force would originate from outgassing jets of sublimating ice, turning into vapor and impelling the nucleus. However, the issue arises here. When comets outgas with sufficient intensity to cause measurable trajectory alterations, they become exceptionally bright. Observers witness massive plumes, extended tails, and dramatic increases in luminosity. 3 Atlas, conversely, was exhibiting the opposite behavior. JPL had predicted an apparent magnitude of approximately 14.8, which is already faint and requires competent amateur telescopes for observation. However, actual readings indicated the object's magnitude was 15.1, about 26% dimmer than expected. This is counterintuitive. If the outgassing were strong enough to displace the object 1 million kilometers off course, we should be witnessing the brightest interstellar comet on record. Instead, it is fainter than predicted, despite the James Webb Space Telescope confirming it is shedding approximately 25 kilograms of water every second. Thus, we have an object deviating from its predicted path in a manner suggestive of forward propulsion, while simultaneously appearing dimmer than anticipated, even with confirmed active outgassing. These facts do not readily align with standard cometary behavior, creating a tension that astronomers are attempting to resolve with increasingly inventive explanations. Some have proposed that the nucleus's rotation might be oriented in such a way as to conceal the primary active regions from Earth's view. While plausible, this explanation is notably convenient. Others point to the compositional anomalies detected by the KEK Observatory in August, specifically the unusual nickel emissions without corresponding iron and the remarkably low water content for an active comet. Perhaps this object's chemistry is so dissimilar to solar system comets that it behaves in ways for which we currently lack models. This is also a possibility, considering interstellar comets are rare, and we have studied only 3. It is conceivable that our assumptions about their behavior are simply incorrect. However, a third explanation exists, one that most mainstream astronomers are reluctant to discuss publicly, but do so privately. What if the deviation is not random? What if 3 Atlas possesses the capability to adjust its trajectory, not through natural outgassing that coincidentally points in a favorable direction, but through a more deliberate mechanism? Avi has been asserting this for months, ranking the object at 4 out of 10 on his scale of potential technological origins. He argues that the accumulation of anomalies reduces the probability of natural explanations below acceptable thresholds. Each oddity individually can be explained, but collectively, they begin to resemble a pattern. The tracking community is not in unanimous agreement. Some groups have attempted to replicate the Earth exists findings and claim they cannot confirm the same magnitude of deviation. Others suggest their data indicate similar trends, but attribute them to outdated orbital elements within the JPL database. Orbital elements are the mathematical parameters defining an object's trajectory through space, refined with additional observations. It is possible that JPL's last update was on October 10th, and by October 21st, these elements had become sufficiently stale to produce prediction errors. Except, JPL regularly updates orbital elements for near-Earth objects and significant comets, especially for an object as prominent as 3 Atlas. The notion that they would allow the data to become outdated by 11 days during its approach to perihelion seems improbable, as this is precisely the period when tracking would be most critical, with observatories worldwide focusing instruments on the object and NASA coordinating observations from Mars orbiters, the Hubble Space Telescope, James Webb, and ground-based facilities across multiple continents. David Sarita, another independent researcher, further fueled this specific discussion on October 20th. He was reviewing images from NASA's LASCO C3 coronagraph, a solar telescope designed to observe the sun's corona by obscuring the bright solar disk. LASCO captures images of the space surrounding the sun, and comets occasionally traverse its field of view. Sarita documented something unusual. In multiple frames, 3 Atlas appeared to exhibit geometric light structures, not the diffuse circular glow typical of a comet's coma, but sharp-edged patterns. In one image, the glow formed what he described as a cross-like plasma geometry before the object disappeared from the subsequent frames, only to reappear and then vanish again. It must be noted that LASCO images are notoriously difficult to interpret. One is observing extremely faint objects through a coronagraph designed for solar observation, not deep space imaging. Artifacts are common. Image processing can create false patterns, and cosmic rays striking the detector produce bright spots, while spacecraft telemetry errors can result in data gaps. Skeptics immediately attributed these factors to these issues. What Sarita identified as geometry, they labeled as noise. However, this claim became harder to dismiss for a crucial reason. Earth Exists had conducted their own analysis of 3 Atlas using single image enhancement techniques without stacking or processing beyond basic contrast adjustments. They observed similar patterns: green outer edges, a blue core, and pink zones arranged in distinct geometric sections. They compared these observations to reference stars within the same field of view, including Spare and Comet C 2025 R2 Swan. These comparison sources appeared perfectly circular, exhibiting standard stellar symmetry. 3 Atlas did not. The coloration observed aligns with spectroscopic analysis conducted by the KEK Observatory in August, indicating emissions of cyanogen, ionized nickel, and hydrogen plasma. Each element emits light at specific wavelengths, producing distinct colors when the spectrum is analyzed. However, these emissions typically mix into a diffused glow. The assertion here is that they are spatially segregated into defined zones, as if the plasma surrounding the object is somehow structured rather than random. This would be consistent with controlled magnetic fields organizing charged particles, a phenomenon observed around fusion reactors or magnetized spacecraft, not a ball of icy debris. It is imperative to exercise caution here. Extraordinary claims necessitate extraordinary evidence, and currently, we have provocative observations from non-institutional sources. This does not inherently render them incorrect. Citizen science possesses a strong track record, with amateur astronomers discovering comets, tracking asteroids, and even identifying exoplanet transits. However, it does mean that these findings require independent verification from facilities equipped with calibrated instruments and employing peer-reviewed methodologies. To date, major observatories have not released data confirming or refuting these specific claims of geometric patterns. What we have observed is silence, or more accurately, delayed releases. The Mars Reconnaissance Orbiter's high-rise camera was scheduled to image 3 Atlas during its closest approach to Mars on October 3rd. Images from this instrument, with a resolution of approximately 30 kilometers per pixel, could potentially reveal surface structural details and even confirm whether the brightness distribution aligns with natural outgassing or a more organized source. As of October 23rd, these images have not been publicly disseminated. NASA has cited the government shutdown as the reason for these delays, but this explanation has been met with unease by many observers. This is arguably the most significant interstellar object to traverse the inner solar system in recorded history, and data is being withheld during the most critical observation period. It is possible that there is nothing unusual in these images, that high-rise captured precisely what one would expect, a fuzzy object with a tail, and NASA has simply not yet processed and released the files. Alternatively, what they observed might require careful analysis, consultation, and verification before public disclosure. We do not know, and this uncertainty creates fertile ground for speculation to proliferate. What we do know, what is documented and verifiable, is that multiple independent groups employing different methods claim 3 Atlas is not adhering to its predicted gravitational path. The measured deviations, if accurate, would necessitate forces beyond simple solar radiation pressure or symmetrical outgassing. These forces would need to be directed, sustained, and considerably more powerful than typically observed from comets of similar size and activity levels. All of this is occurring during the final week preceding perihelion, the period when the object will pass behind the Sun and become entirely unobservable from Earth. On October 29th, 2025, at 1.356 astronomical units from the Sun, it will be hidden in solar glare. If one were designing a trajectory to execute a course correction undetected, one could not select a more opportune moment. The Oberth effect, named after Hermann Oberth, postulates that the most energy-efficient time for a spacecraft to engage its engines is at the point of maximum velocity, typically at perihelion. A minor thrust applied when moving at high speed results in a significantly greater change in orbital energy compared to the same thrust applied when moving slowly. Thus, we find ourselves in a position where an object exhibits a growing positional anomaly, displays geometric light patterns that may or may not be genuine, and shows a dimming trend that contradicts its confirmed activity. Furthermore, in 7 days from the October 21st observation, it will disappear behind the Sun precisely when an intelligent system would strategically choose to make its move. The mathematics align perhaps too perfectly. The timing feels excessively convenient, and the absence of clear explanations from official sources creates a void that speculation readily fills. By November 3rd, 3 Atlas will re-emerge. We will then observe whether the anomaly persists, increases, or dissipates. We will ascertain if October 29th was merely another perihelion passage, or if something utilized those 8 obscured days to adjust its course. Until then, we are left with data that does not quite reconcile, observations that do not fully align, and a growing apprehension that the universe might soon remind us of the limited extent of our understanding. SETI Protocols Update, October 16th, 2025. The Declaration of Principles Concerning Activities Following the Detection of Extraterrestrial Intelligence has remained largely unchanged since 1989. This formal document, endorsed by 6 international space and astronomy organizations, outlines the procedures scientists should follow upon detecting a signal from an alien civilization: independent verification, notification of the United Nations, Secretary General, open data sharing, and prohibition of a reply without international consultation. These principles have guided SETI research for over 3 decades, with only minor updates in 2010 to refine language and clarify procedures. On October 16, 2025, the International Academy of Astronautics SETI Committee published a comprehensive revision. This was not a series of minor adjustments, but a complete overhaul, expanding the scope, updating protocols for contemporary technology, and introducing new requirements not present in earlier versions. The timing of this release, coinciding with the period when 3 Atlas is generating maximum public interest and scientific debate, has not gone unnoticed. The revised protocols have been in development for years. A task group was formed in 2022 to examine how SETI should adapt to evolving information environments, broadened search methodologies, and increased international participation. They presented a draft at the International Astronomical Congress in Milan in 2024, gathered feedback, refined the document, and brought it to a final vote at the International Astronautical Congress in Sydney in late September 2025. The October 16th publication represents the formal release following that vote, with full adoption anticipated before the end of the year. However, perception plays a role as significant as reality and public discourse. To casual observers, the updating of SETI's first contact protocols precisely when an anomalous interstellar object is approaching perihelion appears to be preparation for an imminent event. Conspiracy communities have swiftly connected these dots, interpreting it as evidence that SETI possesses prior knowledge and is mobilizing accordingly. The protocols, they argue, needed immediate updating, not a postponement to the following year, because something significant might transpire in the coming months, necessitating these new frameworks. The more conventional explanation involves bureaucratic timing. International committee work progresses at a deliberate pace. The September International Astronautical Congress meeting in Sydney was the scheduled venue for voting on the revised document, irrespective of 3 Atlas's celestial movements. The October publication adheres to standard academic practice of releasing papers shortly after conference presentations. The correlation with 3 Atlas's perihelion is thus a coincidence, not a coordinated effort. However, the document itself subtly challenges this benign interpretation. The preamble explicitly references artificial intelligence, social media, and political instability as factors influencing how detection announcements will be managed. It acknowledges that misinformation spreads more rapidly than verification, that state and non-state actors may exploit discovery claims for political advantage, and that protecting researchers from harassment has become essential. These are not abstract concerns. They are direct responses to the current information landscape, where discussions surrounding 3 Atlas already exemplify every challenge the protocols aim to address. The new framework extends beyond radio signals. Previous versions concentrated almost exclusively on electromagnetic transmissions, embodying the classic SETI paradigm of listening for intentional broadcasts from distant civilizations. The 2025 revision encompasses techno-signatures of any kind, including laser pulses, waste heat emanating from megastructures, chemical biosignatures detected in exoplanet atmospheres, and physical artifacts. This last category represents a novel and significant addition. Physical artifacts imply objects such as 3 Atlas. The current protocols now clearly encompass situations where a discovery is not merely a signal, but a tangible, manufactured entity that is encountered directly. The most debated modification is Principle Number 7. It unequivocally mandates that pending comprehensive international discussions, no response shall be issued to a confirmed detection. Prior versions alluded to consultation, but lacked clarity on its mandatory nature. The revised text is definitive. Refrain from replying. Consult first. Such consultations must be conducted through the United Nations Committee on the Peaceful Uses of Outer Space or other globally representative international bodies. No single nation, organization, or individual possesses the authority to speak on behalf of all humanity. This signifies a substantial alteration in the distribution of authority. Under the former guidelines, the entity responsible for detecting a signal held considerable latitude in determining the response. While consultation was encouraged, it was not a binding obligation. The updated protocols impose stronger normative expectations against independent actions. Should a detection occur and a response be sent without United Nations involvement, it would constitute a breach of internationally recognized scientific standards. While not a legal prosecution, this carries significant reputational and professional ramifications, which can be equally potent within academic and governmental spheres. Principle Number 8 addresses ethical and legal considerations, stipulating the need to assess potential repercussions on human society, ensure the protection of discoverers from harassment, and adhere to the legal frameworks governing space activities. This principle was absent in previous iterations. Its inclusion acknowledges that detections will transcend purely scientific events, encompassing political, social, and potentially perilous dimensions for the individuals involved. Scientists who ascertain the existence of extraterrestrial intelligence might face threats to their lives, undue pressure from governmental entities, intense media scrutiny, or even graver consequences. The protocols now formally recognize this inherent risk and advocate for protective measures. Furthermore, the document establishes a dedicated post-detection subcommittee within the ILA SETI committee. This standing body will provide assistance and guidance in the event of a detection, offering specialized knowledge in areas such as interpretation, communication strategies, and the management of broader societal implications. The existence of this structure prior to a detection ensures that responses will not be improvisational. It provides institutional memory, pre-established procedures, and designated experts, marking the difference between pandemonium and organized action. A subtle yet significant refinement pertains to data archiving. The new protocols mandate that evidence be preserved in multiple geographic locations using methods that prevent tampering. Blockchain technology is explicitly mentioned. The underlying concern is the potential for data manipulation, either by discoverers who might falsify evidence or by external parties seeking to suppress or alter genuine findings. The distribution of encrypted, time-stamped copies of raw data across numerous secure repositories renders manipulation virtually impossible. Any individual can then verify the original data against the archived copies. This level of data security was not a necessity in 1989. At that time, the threat model was considerably simpler. The focus was on false positives, instrumental malfunctions, and the misinterpretation of natural phenomena as artificial signals. The risks of deepfakes, AI-generated false data, coordinated disinformation campaigns, or governmental suppression of discoveries were not primary concerns. The advent of the Internet has fundamentally altered this landscape. The revised protocols reflect this new reality. Another enhancement is frequency protection. Should a detection be made via electromagnetic transmission, the updated protocols call for a petition to the International Telecommunication Union to safeguard the pertinent frequency band from interference. This provides a legal mechanism to prevent terrestrial broadcasts that could disrupt or overwhelm the detected signal. It is a pragmatic measure that also underscores the seriousness of the situation. Allocating international radio spectrum protection signifies a commitment to treating the detection as genuine and of paramount importance. The collaborative process that informed these revisions is particularly noteworthy. The task group did not operate in isolation. They employed surveys, workshops, and actively engaged early career SETI researchers who will be responsible for implementing these protocols in the future. Remarkably, they even utilized ChatGPT for feedback analysis, a detail explicitly documented in the publication. This demonstrates exceptional transparency regarding their methodology, while also recognizing the pervasive influence of artificial intelligence in contemporary scientific endeavors. To formulate protocols for detecting alien intelligence, it is imperative to acknowledge that human intellect is already augmented by artificial systems. Critics have raised the point that protocols, irrespective of their meticulous drafting, lack enforcement mechanisms. SETI operates within a scientific community, not a governmental structure. The Declaration of Principles is voluntary. Signatories commit to adherence, but no penalties beyond reputational damage exist for non-compliance. If an independent researcher or nation-state were to detect a signal and respond without consultation, the protocols cannot legally compel them to refrain. They can only exert social and professional pressure against such conduct. However, this pressure is not insignificant. The scientific enterprise is fundamentally built upon reputation. The violation of widely accepted ethical standards can lead to the termination of careers, damage the standing of institutions, and isolate individuals from collaborative networks. The majority of scientists highly value their professional integrity. The revised protocols leverage this intrinsic motivation to foster incentive structures that promote responsible behavior, even in the absence of legal enforcement. The question of timing persists. Why finalize and release the protocols now? The task group's work commenced in 2022, preceding the existence of 3I Atlas. The Milan draft in 2024 predated widespread awareness of the anomalous characteristics of most observed objects. The vote in Sydney in September occurred mere weeks before the object's perihelion. At each stage, the process followed its own internal timeline, independent of any interstellar visitors. Nevertheless, the final publication in mid-October, coinciding with intense global focus on a potentially artificial object traversing our solar system, creates an undeniable perception of connection. Perhaps this perception is beneficial. If 3I Atlas proves to be a natural phenomenon, the protocol update still serves the purpose of future preparedness. However, should observations in November and December reveal something that necessitates the invocation of these protocols, having them freshly revised and publicly accessible ensures that all parties are aware of the established procedures. There is no uncertainty regarding the appropriate next steps. The international community has agreed upon a framework just weeks before it might be required. Skeptics argue that this is mere projection, attributing intent to coincidence. The protocols were undergoing revision irrespective of external events. The publication timeline adhered to academic conventions. The concurrent interest in 3I Atlas does not imply causation. The scientists involved in the protocol revision were not coordinating with the astronomers tracking the object. These are distinct communities with independent workflows that have coincidentally converged in time. However, institutions do communicate with each other. The ILA SETI committee includes members who are cognizant of 3I Atlas. Michael Garrett, the lead author of the revised protocols, is affiliated with institutions engaged in astronomical observation. Catherine Denning, another author, specializes in the anthropological facets of contingent scenarios. These individuals do not operate in informational isolation. They were aware of the object, its anomalies, and the approaching perihelion when they finalized the document. Regardless of whether this knowledge consciously influenced the timing, the outcome remains the same. Humanity approaches the post-perihelion observation period of 3I Atlas equipped with updated, comprehensive protocols for responding to the detection of extraterrestrial intelligence. If these protocols are indeed required, they are ready. If not, they still represent the most thoroughly considered framework ever developed for one of the most significant scenarios imaginable. The document includes a crucial element absent in previous versions: a clear definition of when these protocols are to be applied. They are relevant when evidence indicates intentional transmission or construction by a non-human intelligence. This is not applicable to any anomaly or an inexplicable natural phenomenon. The threshold is evidence of intentionality, design, or purpose. Below this threshold, the activity falls within the realm of intriguing scientific inquiry. Above it, the situation enters the domain of potential contact scenarios, where these protocols become active. 3I Atlas currently resides on this threshold. The 8 observed anomalies suggest something unusual, but do not definitively prove intent. If subsequent observations reveal trajectory alterations inconsistent with natural forces, if radio transmissions are detected, or if secondary objects separate and maneuver independently, then intentionality becomes exceedingly difficult to dispute. At that juncture, these protocols transition from theoretical constructs to operational instructions for managing what could be the most pivotal discovery in human history. The revised protocols will not entirely prevent chaos if such a scenario unfolds, but they will provide structure. They will assign responsibilities, establish communication channels, safeguard researchers, ensure data integrity, and guarantee international involvement, thereby precluding unilateral actions. In a situation where events will be entirely unprecedented and numerous aspects are likely to go awry, having any framework is preferable to complete improvisation. SETI researchers have awaited a detection for decades. The prevailing assumption was that it would manifest as a radio signal from a distant star, light years away, allowing ample time for a measured response without immediate repercussions. 3I Atlas, if it represents a detection, presents a vastly different scenario. It is proximate, it is in our immediate vicinity, and it is currently traversing our planetary system. The timescales for response are measured in weeks, not years. The luxury of protracted deliberation is non-existent. This urgency may explain why the protocols emphasize immediate actions. Independently verify, secure the data, inform the Secretary General. These are not recommendations for long-term strategy, but rather immediate crisis management steps for the acute phase. These actions should be undertaken within hours or days to establish factual accuracy and prevent misinformation from shaping the narrative. Subsequent, longer-term responses can be implemented once initial stabilization is achieved. October 16, 2025. The date SETI updated its contingency plan for contact, 13 days prior to 3I Atlas reaching perihelion, and 18 days before its reappearance from behind the Sun for post-perihelion observations. The protocols are published, voted upon, and ready for implementation. Whether they will be needed is a question that November and December will answer. However, their availability, freshly revised and internationally endorsed precisely when they might be most crucial, represents either extraordinary foresight or extraordinary coincidence. Time will reveal which it is. The phenomenon of disappearing behind the Sun. There is a specific term in orbital mechanics rarely encountered outside of spaceflight or planetary science: solar conjunction. While it sounds technical, almost bureaucratic, its meaning is remarkably straightforward. It occurs when an object in space passes directly behind the Sun from Earth's perspective, rendering it completely invisible to our telescopes due to the Sun's overwhelming radiance obscuring everything in its vicinity. For 3I Atlas, solar conjunction began on October 21st, 2025, the very same day trajectory deviations started appearing in independent tracking data. Consider the geometry for a moment. Earth, the Sun, and 3I Atlas aligned in a straight line, with the Sun positioned in the middle. From our observational standpoint, the object vanished into the solar glare. This is not due to passing behind the physical disk of the Sun, which would require precise alignment down to arc seconds, but rather being close enough that the Sun's corona, its superheated outer atmosphere extending millions of kilometers into space, creates a blinding backdrop that renders observation impossible. Even our most sophisticated coronagraphs, instruments designed specifically to block the Sun's disk and study its surroundings, struggle to detect faint comets when they are this close to solar alignment. This alignment is not permanent. Celestial bodies are in constant motion. Earth orbits the Sun, and the geometric configuration continuously shifts. However, for 3I Atlas, the timing created a unique situation. Solar conjunction on October 21st meant the object entered the unobservable zone 8 days prior to its perihelion. That is, 8 days before its closest approach to the Sun on October 29th at 11:36 Universal Time. These 8 days represent the period during which the object would be accelerating to its maximum velocity and experiencing peak solar radiation. If it were anything other than a natural comet, this would be the most critical phase of its mission profile. Let us consider what occurs at perihelion from an engineering perspective. If one were to dispatch a probe to another star system and intend for it to execute maneuvers within that system, such actions would not be random. They would adhere to the principles of orbital mechanics that have governed spaceflight since humanity first ventured beyond Earth's atmosphere. The Orth effect, formulated in the 1920s, demonstrates that the most efficient time to alter a spacecraft's trajectory is when it is moving at its highest velocity. The underlying mathematics are straightforward. Kinetic energy is calculated as 1/2 of the mass multiplied by the velocity squared. This squared term is of immense significance. If an object is traveling at 10 kilometers per second and an additional 1 kilometer per second of thrust is applied, the resulting energy change is substantially less than if the object were traveling at 50 kilometers per second and the same 1 kilometer per second of thrust were applied. The greater the existing velocity, the more significant the energetic impact from each unit of thrust. For 3I Atlas, maximum velocity is achieved at perihelion. At this point, while descending into the Sun's gravitational well, the object will be traveling at approximately 68 kilometers per second relative to the Sun. If the intention were to release probes capable of intercepting planets within the inner solar system, perihelion would be the opportune moment. A minor alteration in velocity at that juncture, perhaps 10 or 15 kilometers per second in the appropriate direction, could redirect a small probe towards Earth, Mars, or Venus with a relatively modest expenditure of fuel. Delaying such a maneuver until the object is farther out and moving more slowly would necessitate an exponentially greater energy cost for the same maneuver. This is not mere speculation about alien engineering. It is how human spacecraft function. When we dispatch probes to the outer solar system, we utilize gravity assists to gain speed and time our engine burns for moments of peak velocity. The Voyager missions, New Horizons, and every deep space probe operate according to these principles because physics remains indifferent to intentions. The mathematical principles apply identically, whether the endeavor is undertaken by NASA or by an intelligence that evolved under a different star. Now, Let us superimpose that engineering reality onto the timeline of 3I Atlas. October 21st marks the commencement of solar conjunction. October 29th is the perihelion passage at 1.356 astronomical units. During those 8 days, Earth-based telescopes will detect nothing. Mars orbiters might catch brief glimpses if they are precisely positioned at the right moment, but the Sun's orientation relative to Mars limits even those observations. The European Space Agency's JUICE spacecraft, currently en route between Earth and Jupiter on its journey to the outer solar system, will attempt observations in early November. However, during the critical perihelion window, 3I Atlas will operate in what is essentially complete darkness from our observational perspective. The distance of 1.356 astronomical units places it approximately 203 million kilometers from the Sun. For context, Earth orbits at 1 astronomical unit, and Mars at approximately 1.5. Perihelion for 3I Atlas positions it closer to the Sun than Mars' orbit, but farther than Earth's. This location offers immense solar energy for power generation, assuming it were a technological system, without being so close that temperatures would vaporize metals or destroy electronics, provided adequate shielding. A habitat engineered for interstellar operation, shielded against cosmic radiation and near absolute zero temperatures, would find this distance comparatively benign. The solar radiation flux at this distance would deliver approximately 33 gigawatts of power to the object's surface. Assuming Avi Loeb's minimum diameter estimate of 5 kilometers, 33 gigawatts is roughly equivalent to the output of 30 large nuclear power plants. If even a fraction of this energy could be captured and converted into usable power, it would be more than sufficient to operate any conceivable propulsion system, communication array, or manufacturing process. Again, this is not an assertion that 3I Atlas is technological, but rather an observation that if it were, perihelion would represent the ideal moment for it to execute its intended purpose, and solar conjunction would ensure that its activities would go unobserved. The orbital parameters reveal another narrative that can be easily overlooked if one is not actively searching for it. 3I Atlas possesses an eccentricity of 6.137. Eccentricity is a numerical value that quantifies the degree to which an orbit is elliptical or hyperbolic. A perfect circle has an eccentricity of 0. Earth's slightly elliptical orbit has an eccentricity of 0.017. Any value above 1.00 signifies a hyperbolic trajectory, indicating that the object is not gravitationally bound to the Sun and will eventually escape its influence. A value of 6.137 is extraordinarily hyperbolic. The trajectory is nearly linear, with its path being only slightly bent by the Sun's gravitational pull. This object is traversing our solar system at such extreme velocity that even our star's immense gravitational force bends its path only marginally. This extreme eccentricity implies something else as well. The duration of its presence within the inner solar system is minimal. 3I Atlas did not spend months gradually approaching the Sun like comets originating from the Oort cloud. It arrived at breakneck speed from interstellar space at 58 kilometers per second and is expected to depart at approximately the same velocity. The entire transit, from its discovery in early July to its departure from the inner system by late December, spans approximately 6 months. By comparison, long-period comets can spend years within the inner solar system, and short-period comets return every few years or decades. This is a flyby in the most literal sense, a brief encounter with the Sun before continuing its journey into the galactic disk. However, here is where the situation becomes particularly intriguing. The trajectory is not merely hyperbolic, it is aligned. The orbital plane of 3I Atlas closely matches the ecliptic, the plane defined by Earth's orbit around the Sun, to within 5 degrees. Most objects arriving from interstellar space would approach from random angles. The galaxy does not adhere to our ecliptic plane. Comets originating from the Oort cloud, while gravitationally bound to the Sun, arrive from every conceivable direction. This is why they appear scattered across the sky, exhibiting retrograde orbits, prograde orbits, high inclinations, and low inclinations, with no discernible preferred direction. 3I Atlas is different. Its inclination of 175 degrees indicates it is moving retrograde, opposite to the direction in which planets orbit. However, the plane itself is remarkably aligned with ours. Calculations by JAV estimate the probability of such an alignment occurring by chance at approximately 0.2%. This is not an impossible probability, representing 2 in 1,000 instances, but it is uncommon enough to warrant attention. A trajectory aligned with the planetary plane facilitates interception. If the objective were to release probes designed to encounter multiple planets, initiating the journey from a trajectory already within their orbital plane would conserve substantial amounts of fuel compared to executing major plane changes, which are among the most energetically demanding maneuvers in orbital mechanics. Now consider the timing in conjunction with this alignment. The arrival trajectory of 3I Atlas brings it within tens of millions of kilometers of Mars on October 3rd, Venus on November 3rd, and Jupiter on March 16th, 2026. The probability of a random interstellar object coincidentally passing in close proximity to 3 major planets during its flyby is vanishingly small, estimated by Lowe and his colleagues at approximately 0.005%, or 5 in 100,000. While not impossible odds, these figures are accumulating in a manner that triggers pattern recognition in our minds. Is it a coincidence that perihelion occurs during solar conjunction? From a physics perspective, there is no direct correlation. Solar conjunction is determined by Earth's position relative to the object's trajectory. Perihelion refers to the object's closest approach to the Sun. These are independent parameters. The fact that they occur within 8 days of each other, creating a window where the object is simultaneously at peak velocity and obscured from observation, is simply a consequence of the orbital geometry. However, if one were planning an interstellar mission and had the ability to select the approach vector, such a configuration would undoubtedly be designed into the mission profile to conceal the most critical phase behind the system's most luminous celestial body. The orbital parameters present another piece of information that is easily overlooked. 3I Atlas exhibits an eccentricity of 6.137. Eccentricity is a numerical value that defines the shape of an orbit, indicating how elliptical or hyperbolic it is. A circular orbit has an eccentricity of 0. Earth's slightly elliptical orbit has an eccentricity of 0.017. Any value exceeding 1.00 denotes a hyperbolic trajectory, meaning the object is not gravitationally bound to the Sun and will eventually escape its influence. An eccentricity of 6.137 signifies an extraordinarily hyperbolic trajectory, almost a straight line, with its path barely deflected by the Sun's gravity. This object is traversing our solar system at such a high velocity that even the Sun's immense gravitational pull only slightly alters its course. This extreme eccentricity also implies that the time spent within the inner solar system is brief. Unlike comets from the Oort cloud, which may spend years in the inner system, 3I Atlas arrived from interstellar space at 58 kilometers per second and will depart at roughly the same speed. The entire passage, from its discovery in early July to its departure from the inner system by late December, spans approximately 6 months. This contrasts sharply with long-period comets that can remain in the inner system for years, or short-period comets that return every few years or decades. This is a flyby in the truest sense, a fleeting interaction with the Sun before continuing into the galactic disk. However, here is where the matter becomes exceptionally interesting. The trajectory is not only hyperbolic, It is aligned. The orbital plane of 3I Atlas is aligned with the ecliptic, the plane defined by Earth's orbit around the Sun, to within 5 degrees. Most objects arriving from interstellar space would approach from random angles, as the galaxy does not conform to our ecliptic plane. Comets from the Oort cloud, while gravitationally bound to the Sun, originate from every conceivable direction, which is why they are observed scattered across the sky, exhibiting retrograde orbits, prograde orbits, high inclinations, and low inclinations with no preferred direction. 3I Atlas is different. Its inclination of 175 degrees indicates it is moving retrograde, contrary to the direction of planetary orbits. However, the plane itself is remarkably aligned with ours. Calculations by JAV have determined the probability of this alignment occurring by chance to be approximately 0.2%. This is not an impossible occurrence, representing 2 instances out of 1,000, but it is uncommon enough to raise questions. A trajectory aligned with the planetary plane simplifies interception. If the objective were to release probes that could encounter multiple planets, commencing from a trajectory already within their orbital plane would conserve significant fuel compared to executing major plane changes, which are among the most energy-intensive maneuvers in orbital mechanics. Now consider the timing in conjunction with this alignment. The arrival trajectory of 3I Atlas brings it within tens of millions of kilometers of Mars on October 3rd, Venus on November 3rd, and Jupiter on March 16th, 2026. The probability of a random interstellar object happening to pass in close proximity to 3 major planets during its flyby is exceedingly small, estimated by Lowe and his colleagues at approximately 0.005%, or 5 in 100,000. While these odds are not impossible, they are beginning to accumulate in a manner that triggers pattern recognition within our minds. Is it a coincidence that perihelion occurs during solar conjunction? From a physics standpoint, there is no inherent connection. Solar conjunction is dictated by Earth's position relative to the object's trajectory. Perihelion refers to the object's closest approach to the Sun, which are independent parameters. The fact that they occur within 8 days of each other, creating a window where the object is both at peak velocity and hidden from observation, is simply a result of the orbital geometry. However, if one were planning an interstellar mission and could choose the approach vector, such a configuration would undoubtedly be designed into the mission. The most critical phase would be concealed behind the system's brightest object. The critical moment for investigation arrives on November 3rd, when the object designated 3I Atlas will emerge from behind the Sun, allowing for unobstructed observation. With clear lines of sight re-established, numerous astronomical facilities will commence tracking its position, meticulously measuring its luminosity, and performing detailed spectral analysis. Should the trajectory anomalies detected in late October prove to be genuine and persistent, they will undoubtedly be reflected in the data gathered post-perihelion. The deviation from its predicted path should manifest as a more significant offset, with its divergence from purely gravitational motion becoming readily apparent. Conversely, if those observed deviations were attributable to measurement inaccuracies or transient phenomena like outgassing, the object is expected to revert to its anticipated trajectory, thereby dispelling all current conjecture. However, a third, more unsettling possibility persists, one that causes considerable unease among astronomers. What if, subsequent to its perihelion passage, the object's trajectory precisely aligns with predictions, yet its spectroscopic signature undergoes a transformation? What if its composition appears altered? What if its activity level decreases or, conversely, surges unexpectedly? What if its polarization characteristics shift? As publicly stated by Dr. Lowe, should 3I Atlas navigate its perihelion passage intact and continue to exhibit traits characteristic of a natural comet, he intends to reclassify it to rank 2 on his assessment scale. While still considered anomalous and noteworthy, such a designation would strongly suggest a natural origin. However, should observations following its perihelion reveal any irregularities, any indication that the object is no longer the same entity that previously disappeared from view, then a rank of 4 might prove insufficient. Historically, comets have been known to behave erratically around perihelion. They can fracture due to extreme thermal stress, erupt unexpectedly as newly exposed ice vaporizes, or fade rapidly if their supply of volatile materials is depleted. Comet Ison, in 2013, underwent complete disintegration during its perihelion passage, offering a stark illustration of the violent nature of these solar encounters. Yet, Ison's trajectory brought it much closer, grazing the Sun's surface at a mere 1 million kilometers. In contrast, 3I Atlas is maintaining a considerably safer distance of 203 million kilometers, a separation ample enough to mitigate thermal stresses, even for a loosely aggregated collection of debris. Mass estimations suggest a robust object, potentially weighing at least 33 billion tons, inferred from the absence of significant non-gravitational acceleration despite observable outgassing. This substantial mass, coupled with an estimated diameter of approximately 5 kilometers, implies an object possessing either exceptional density or remarkable structural integrity. Most comets are comprised of loosely bound ice and rock, forming porous structures that readily sublimate and shed material. If 3I Atlas is indeed this massive and has not exhibited trajectory shifts due to outgassing, 2 scenarios emerge. Either the outgassing is perfectly symmetrical, a highly improbable situation given the observed anti-tail in July and August, or the object's sheer mass renders any recoil from even vigorous outgassing negligible. In either case, it appears engineered for longevity. A perihelion passage at 1.356 astronomical units is unlikely to cause its demise. The pivotal question lies in its behavior during those concealed days behind the Sun. Will it fragment naturally, producing debris that will become visible as it disperses over the ensuing weeks? Will it deliberately eject material, perhaps smaller bodies embarking on their own trajectories towards specific destinations? Or will it simply continue along its hyperbolic path, unaltered except for the anticipated increase in brightness and potential escalation of outgassing due to solar heating? We are poised to discover the answer. By the time November arrives, 32nd Atlas will have completed its close solar encounter, absorbed an estimated 33 gigawatts of solar radiation over several days, and, if it deviates from being a natural comet, executed any pre-planned maneuvers or deployments intended for this juncture. The subsequent observations will either validate its natural origin, revealing no anomalies despite prior irregularities, or they will present evidence compelling us to seriously consider the technological hypothesis. There is no longer a middle ground. The data will either unequivocally support natural explanations, or it will not. And somewhere between Earth and that hidden point behind the Sun, during the 8 days when no telescope can observe it, 3E Atlas will perform its intended function. The enigma of its brightness presents a key area of inquiry. In astronomy, brightness is not merely a measure of light intensity reaching an instrument. It serves as a diagnostic tool, offering insights into an object's composition, its level of activity, and the extent of its surface exposed to solar radiation. When a comet approaches the Sun, predictable phenomena occur. Ice transitions directly from solid to gas through sublimation. This gaseous release carries dust particles away from the nucleus, forming the characteristic coma and tail. The coma then scatters sunlight, augmenting the comet's apparent brightness. The closer the proximity to the Sun, the more intense the heating, leading to increased sublimation and a brighter visual display. This relationship is so well established that astronomers can forecast a comet's brightness months in advance with considerable accuracy. 32nd Atlas, however, deviated from this established pattern. Predictions issued by the Jet Propulsion Laboratory, based on conventional cometary models and the object's known dimensions and trajectory, anticipated an apparent magnitude of approximately 14.8 in late October. Magnitude is a logarithmic scale where lower numbers signify greater brightness. The difference between magnitudes 14 and 15 might seem minor, but each full magnitude increment corresponds to a roughly 2.5-fold increase or decrease in light intensity. Consequently, the observed magnitude of 15.1 indicates the object was approximately 26% dimmer than predicted. This discrepancy might appear slight, as comets are inherently unpredictable. Their activity levels fluctuate, rotation can alternately conceal and expose active regions, and dust production varies with composition. These factors introduce inherent uncertainty into brightness projections. However, what makes this particular dimming so perplexing is the corroborating evidence from the James Webb Space Telescope, which confirmed active outgassing. Spectroscopic analysis revealed the expulsion of carbon dioxide, water vapor, carbon monoxide, cyanide, and ionized nickel from the nucleus. The production rates recorded by Webb suggested the object was shedding material at a rate of approximately 25 kilograms per second during observations in late August. This rate is inconsistent with a dormant comet. It indicates an active system expelling material at levels comparable to many comets within our solar system. Such significant outgassing generates a substantial coma, a diffuse cloud of gas and dust enveloping the nucleus, which then scatters sunlight. A denser coma leads to more scattering and a brighter appearance from Earth. Standard photometric models account for this phenomenon. They measure gas production rates, estimate dust-to-gas ratios using spectroscopic data, calculate the amount of sunlight scattered by this dust, and predict the resulting brightness. For 30-second Atlas, these calculations pointed to a magnitude of 14.8. Instead, telescopes registered 15.1. The most immediate explanation considered is composition. Perhaps 32 Atlas possesses an unusually low dust-to-gas ratio. Pure gas scatters visible light less effectively than dust particles. If the object is ejecting primarily volatile compounds with minimal particulate matter, its coma would be less reflective than anticipated, resulting in a dimmer appearance despite high observed activity. This explanation is plausible. Interstellar comets may originate under conditions distinct from those within our solar system, with differing temperatures, pressures, and chemical environments potentially yielding objects with atypical ice-to-dust ratios. However, Webb's spectroscopic analysis did detect signatures of dust, including silicates and organic compounds, particulate matter that should effectively scatter light. The spectrum did not solely represent a gaseous coma. Solid material was evidently present. Therefore, the hypothesis of a low dust content is not entirely satisfactory unless the dust grains themselves are significantly smaller than those typically found in comets. Extremely small particles, smaller than the wavelengths of visible light, scatter light less efficiently. This could account for reduced brightness even in the presence of confirmed dust. While possible, this explanation necessitates the addition of another unusual characteristic to an already anomalous object. A second potential explanation relates to geometry and viewing angle. Comets are not uniformly spherical. They exhibit jets, localized zones of intense activity where sublimation is concentrated. If the primary active regions on 3-through Atlas are oriented away from Earth, we might be observing primarily the reflected sunlight from the nucleus itself, rather than the intense scattered light from the dusty coma. This scenario occasionally occurs with solar system comets. An active comet can appear relatively faint from Earth if viewed from an unfavorable angle. However, we have confirmation of a visible coma. Hubble images from July depicted a distinct teardrop-shaped envelope of material trailing the nucleus. Furthermore, the anti-tail observed throughout August demonstrated asymmetric outgassing of sufficient strength to to create a visible structure pointing towards the sun. If the jets were vigorous enough to generate these features, they should logically contribute to the integrated brightness measurements. The viewing angle hypothesis would only hold if the object's geometry shifted dramatically between the Hubble observations in July and the brightness measurements in October, and there is no apparent reason for such a change. Then there is the possibility of surface modifications. Comets can develop insulating crusts, layers of dust and organic material that diminish sublimation rates as the surface temperature rises. Fresh ice sublimates rapidly upon initial exposure to solar radiation. Over time, the most volatile ices are depleted, leaving behind a residual layer of less volatile material that acts as an insulating blanket, slowing heat transfer to subsurface ice. This process causes comets to fade as they age. An interstellar comet, having potentially spent billions of years in deep space at temperatures near absolute zero, might possess all its volatile surface ice concealed beneath such a crust. As it approaches the sun, this crust heats up, but this does not necessarily translate to a proportional increase in activity. The object could be outgassing vigorously from localized fissures or weak points, while the majority of its surface remains inert. This scenario aligns with some observations. High activity in specific areas contributing to the observed mass loss, but an overall dim appearance because a significant portion of the surface is not contributing to the coma. This is a plausible natural explanation. However, it raises another question. If the surface is largely inactive, from where is the substantial amount of carbon dioxide originating? Webb detected significant carbon dioxide production, considerably exceeding the water production rate. The sublimation of carbon dioxide requires specific temperature thresholds, suggesting either exposed carbon dioxide ice or subsurface reservoirs connected to the surface via cracks or vents. In either case, one would anticipate localized brightening around these active zones, hotspots that should be discernible in high-resolution imagery. The High-Resolution Imaging Science Experiment, HiRISE, observations from the Mars Reconnaissance Orbiter could potentially resolve this issue. With a pixel scale of approximately 30 kilometers, HiRISE should be capable of differentiating between a uniformly dim object and one featuring bright active regions concentrated in specific areas. However, these images remain unpublished. Without them, we are left to infer structural details from integrated brightness measurements and low-resolution spectroscopy, attempting to construct a three-dimensional model from two-dimensional data. There is another perspective to consider, one that might sound akin to conspiracy theory, but logically emerges from the data itself. What if the object is deliberately minimizing its apparent brightness? This notion seems preposterous for a natural celestial body. Comets lack intentionality. They react to solar heating in accordance with the principles of thermodynamics. However, if 3/3 Atlas were an artificial construct, a probe or spacecraft rather than a comet, brightness management would constitute a fundamental operational parameter. Consider the design of human spacecraft. Surfaces are coated with specific materials to regulate thermal properties and minimize reflectivity when required. Stealth satellites employ low albedo coatings to reduce visibility. If one were to dispatch a probe across interstellar space with the objective of traversing a planetary system undetected, or at least without drawing undue attention, it would be designed to resemble natural debris, while achieving a natural appearance through spectroscopic analysis, exhibiting appropriate chemical signatures, is less challenging than perfectly matching brightness curves. Intentional outgassing of water and carbon dioxide can mimic cometary activity. Precisely controlling the magnitude at which an object appears necessitates either a perfect replication of surface properties or deliberate dimming through geometric orientation, positioning reflective surfaces away from observers. I acknowledge the extraordinary nature of this suggestion. We are potentially leaning towards technological explanations for what could simply be an unusual but natural comet possessing atypical composition and structure. The brightness paradox, in isolation, provides no definitive proof. Comets frequently surprise us. They flare unexpectedly, fade without warning, fragment into multiple pieces, and exhibit jets that defy conventional modeling. The fact that 33 Atlas is dimmer than anticipated is not by itself an extraordinary occurrence. However, when viewed in context, an object dimmer than expected despite confirmed high activity, exhibiting trajectory deviations from predicted paths, displaying geometric light patterns potentially indicative of structured plasma fields, possessing compositional anomalies such as nickel emissions without corresponding iron, and arriving on a trajectory optimally aligned with the planetary plane and timed for multiple planetary flybys, the picture becomes more complex. Each individual piece of evidence is explainable, but collectively, they form a pattern that is more difficult to dismiss. Brightness measurements will continue through early November as 33 Atlas reappears from behind the Sun. Observatories worldwide will monitor its magnitude, anticipating the expected post-perihelion brightening. Conventional comet models predict significant increases in brightness after perihelion, as fresh material is exposed and outgassing intensifies due to solar heating. If 33 Atlas conforms to this pattern, brightening to a magnitude of 12 or 11 as some predictions suggest, it would lend support to natural explanations. The dimness observed in October could then be attributed to viewing geometry or a temporary reduction in activity. However, if the object remains dimmer than predicted, if its observed brightness continues to fall below expectations despite its proximity to the Sun and confirmed outgassing, then we are confronted with a sustained anomaly demanding further investigation. Consistent dimming suggests inherent characteristics of the object's structure or behavior that current cometary models fail to encompass. This implies either a fundamental misunderstanding of interstellar comet composition or that 33 Atlas is actively managing its observable signature in ways unprecedented for natural objects. Polarization measurements introduce an additional layer of complexity. In late September, the Very Large Telescope (VLT) team observed 33 Atlas and detected extremely negative polarization values. Polarization describes the orientation of light waves after scattering off particles. Different materials and particle sizes produce distinct polarization signatures. Most comets exhibit positive polarization, where the scattered light waves align perpendicularly to the plane of scattering. 30 Sin. Atlas displayed strong negative polarization, with waves aligned parallel to the scattering plane. This behavior is virtually unprecedented in comets. The VLT team noted that the probability of such extreme polarization occurring naturally in a comet is less than 1%. Negative polarization can arise under specific conditions of particle size distribution and composition. Laboratory studies have demonstrated this with certain types of dust produced under controlled environments. However, observing it in an active comet, where particle sizes vary considerably and composition is mixed, is extraordinarily rare. This suggests either that the dust ejected by 33 Atlas is remarkably uniform in size, with all particles clustered around a specific diameter conducive to producing negative polarization, or that its composition includes materials with unusual optical properties not commonly found in solar system comets. A third possibility exists. The polarization might not originate from scattered sunlight at all, but rather from emission resulting from another process that coincidentally produces polarized light. Synchrotron radiation, generated by charged particles spiraling within magnetic fields, produces highly polarized emission. Certain plasma processes also exhibit this characteristic. If what we are observing is not reflected sunlight, but emission from a magnetized plasma surrounding the object, the polarization signature would differ significantly from that of typical cometary dust scattering. This line of reasoning is speculative, venturing into explanations that necessitate exotic physics or technological processes. Nevertheless, When conventional models prove inadequate for explaining observations, alternative hypotheses must be considered. The brightness paradox cannot be definitively resolved through observation alone. It requires close-up imaging, resolved surface features, and thermal mapping to pinpoint heat generation and radiation sources. We need to discern whether we are dealing with a cold, predominantly inactive surface exhibiting localized hotspots, or a uniformly active surface that is somehow inexplicably dimmer than expected. The distinction is of paramount importance in determining the true nature of 33 Atlas. For the present, we can only observe and await further developments. November 3rd marks the resumption of visibility. December 19th will bring its closest approach to Earth at a distance of 1.8 astronomical units, approximately 269 million kilometers. This proximity will be insufficient for amateur telescope observation, but professional facilities will possess excellent viewing geometry. The brightness curve throughout November and December will reveal whether the dimness observed in October was an anomaly or a persistent characteristic. If the object brightens as predicted, conforming to standard cometary behavior, the anomaly will recede into statistical noise. However, if it remains dim, or even becomes dimmer, while maintaining high outgassing rates, then we face a situation that defies straightforward explanation. The universe is replete with phenomena that we do not fully comprehend. Interstellar space is vast and ancient, harboring conditions that are challenging for us to replicate or study. The unusual nature of 33 Atlas does not inherently render it artificial. However, its unusual characteristics aligning with predictable patterns, coincidentally mirroring the design specifications for efficient traversal of a planetary system while minimizing detection, transforms it from merely unusual into something far more profound. Geometric plasma structures, known as the fourth state of matter after solid, liquid, and gas, are formed when gases are heated to the point where electrons separate from atoms, creating a charged particle soup with distinct behavioral properties. Lightning and the sun's corona are examples of plasma. The aurora borealis, a stream of plasma interacting with Earth's magnetic field, is another. Plasma is ubiquitous in the universe, comprising 99% of visible matter, yet it is notoriously difficult to control. Plasma responds to electromagnetic fields, flows along magnetic field lines, and forms structures and instabilities that challenge our most advanced physical models. Natural plasmas encountered in cometary environments are inherently chaotic. The solar wind, a stream of charged particles emanating from the sun at hundreds of kilometers per second, interacts with a comet's coma. This interaction generates a bow shock, a boundary where the solar wind decelerates and compresses. Behind this shock, complex turbulence, eddies, and irregularities emerge. The result is a diffuse, irregular glow. When comets are imaged at specific wavelengths, asymmetries and brighter regions where outgassing is more intense may be observed, but the overall light distribution is typically smooth, following the density gradients of gas and dust within the coma. What is not commonly observed are distinct geometric structures, sharp boundaries, color separation into discrete zones, cross patterns, or other regular shapes. The underlying physics does not typically support such formations. Plasma, in the absence of strong external organizing forces, tends to diffuse and spread, following pressure gradients and magnetic field lines that are themselves often tangled and irregular around comets. The formation of structured geometry necessitates either highly specific environmental conditions or active field management. On October 20th, David Sarita reviewed images captured by NASA's LASCO C3 coronagraph. These instruments are designed to photograph the space surrounding the sun by employing an occulting disk to block the direct light of the solar disk, thereby revealing the faint solar corona and any objects traversing the field of view. Celestial wanderers, known as comets, periodically grace our skies, typically appearing as hazy orbs with luminous streams extending away from the sun. Sarita, during their observations, identified 3 instances of the object designated 32 Atlas across several captured images. What truly captured their attention was not merely the object's presence, but its peculiar visual characteristics. In one particular frame, the way light radiated around the 3 Atlas formations created a distinct cross-like configuration. This was not a precise geometric shape akin to what one might sketch on graph paper, but rather a clear display of 4-fold symmetry, with brighter zones radiating outwards in perpendicular directions. Subsequently, within the following sequence of frames, the object completely vanished. The instrument, LASCO, captures images at predetermined intervals, typically ranging from 12 to 30 minutes, depending on the specific observation protocol. Objects situated within the coronagraph's field of view are expected to remain visible in consecutive captures as they traverse through space. While their brightness might fluctuate slightly due to variations in viewing geometry or inherent activity, they do not typically disappear and then reappear unless an extraordinary event occurs. Yet, the 3 Atlas instances were observed to vanish for multiple intervals again. This perplexing pattern recurred several times throughout the observation period. Sarita meticulously documented these findings and subsequently disseminated them to the public, positing that the sudden disappearances coupled with the geometric formations suggested an unconventional behavior or structure of the object. Skeptics, however, were quick to propose alternative explanations. The images acquired by LASCO present considerable interpretive challenges. The instrument was not originally engineered for deep space observations. Rather, it is optimized for studying the solar corona. Consequently, its sensitivity and calibration are precisely adjusted for specific ranges of brightness and wavelengths. Faint objects nearing the detection threshold can intermittently appear and disappear due to artifacts introduced during image processing, the impact of cosmic rays on the detector, or simply fluctuations in the signal-to-noise ratio. If the 3 Atlas were positioned at the very edge of LASCO's detection capabilities, variations in the background noise from one frame to the next could render it visible in some images while making it invisible in others. The observed cross pattern could potentially be a diffraction artifact. Coronagraphs employ intricate optical systems, incorporating multiple occulting disks and baffling mechanisms to obscure the intense glare of the sun. Bright point sources can, under certain circumstances, generate cross-shaped diffraction spikes due to the edges of these optical components. Stars observed in LASCO images frequently exhibit this characteristic pattern. It is plausible that if the 3 Atlas possessed a bright central core, a concentrated nucleus, or a particularly reflective surface area, it could, in theory, produce similar diffraction effects. However, Earth exists, a collective that meticulously documented trajectory anomalies, conducted an independent analysis. Their investigation did not rely on LASCO imagery. Instead, they processed their own observational data gathered from ground-based facilities, utilizing standard astronomical CCD cameras affixed to telescopes of moderate aperture. They applied single-image enhancement techniques, adjusting contrast and brightness to accentuate faint details, but they refrained from employing multi-exposure stacking or intensive processing methods that might inadvertently generate artifacts. Their captured images revealed color segmentation within the object's coma. The outer regions displayed a greenish hue, the central areas appeared blue, and pink zones were distributed around the nucleus. To ascertain whether this chromatic separation was an artifact, they imaged reference stars within the same field of view. Spiker, one of the brightest stars observable from Earth, presented as a sharply defined circular point spread function, exhibiting a normal color balance. Comet C 2022 S2, SWAN, another active comet visible in the same sector of the sky, displayed a typical cometary appearance, characterized by a diffuse, circular coma and a faint tail. There were no geometric patterns or unusual color separations beyond the subtle greenish tint commonly observed in cometary comas attributed to diatomic carbon emission. The 3 Atlas, however, presented a strikingly different appearance. The color zones they measured corresponded precisely to known emission lines. The green coloration originated from ionized cyanogen, the blue from hydrogen plasma, and the pink was likely a result of a mixture of ionized carbon and other elemental species. These chemical constituents are not unexpected. The KEK Observatory had previously confirmed the presence of cyanogen in August. Hydrogen emission is a standard characteristic of comets. What is truly unusual is the spatial distribution of these emissions. Typically, these emission regions overlap significantly. The gases tend to mix as they expand outward from the nucleus, precluding distinct separation. Turbulence, interactions with the solar wind, and thermal diffusion rapidly blur any initial structural organization within seconds to minutes after material is released from the surface. The maintenance of distinct color zones would necessitate a phenomenon that effectively prevents this mixing. In laboratory plasma experiments, this role is usually fulfilled by a magnetic field. Charged particles tend to spiral along magnetic field lines, remaining confined within specific regions dictated by the field's geometry. If magnetic fields are strategically arranged, it is possible to create structured plasmas with clearly defined boundaries between zones of differing temperatures or compositions. This principle is applied in fusion reactors and in the plasma thrusters utilized for spacecraft propulsion. Such configurations require active field coils or permanent magnets arranged in precise arrangements. Natural magnetic fields surrounding comets are generally weak and irregular. Comets lack internal dynamos, unlike planets, and are not sufficiently massive or electrically conductive to generate robust, self-sustaining magnetic fields. They do, however, contain embedded magnetic fields imprinted from their formation environment, but these fields are typically chaotic and lack large-scale organization. The solar wind also carries its own magnetic field, but this is equally disorganized at the small scales relevant to cometary comas. Could the 3 Atlas possess an exceptionally strong or well-organized intrinsic magnetic field? This possibility cannot be entirely dismissed. If the object originated in an environment characterized by strong ambient magnetic fields, perhaps in proximity to a massive star or within a molecular cloud exhibiting aligned magnetic fields, it might have retained some degree of that structure. Certain minerals, such as magnetite, are known to preserve magnetic fields over geological timescales. If the 3 Atlas exhibits a high concentration of magnetic minerals, and these minerals are aligned, it could theoretically result in a weak yet organized magnetic field. However, this explanation encounters a significant challenge. The field would need to be sufficiently potent to organize plasma over distances spanning hundreds to thousands of kilometers. The scales under consideration are not confined to the nucleus itself, which might measure between 5 and 10 kilometers in diameter. Instead, they encompass the coma, the diffuse envelope of gas that can extend tens of thousands of kilometers for active comets. Generating structured plasma at these vast scales would necessitate field strengths far exceeding what remnant magnetization within rock could provide. This would imply active generation, involving current loops and moving charged particles, creating magnetic fields through electromagnetic induction. An alternative interpretation suggests that the observed phenomena are not indicative of plasma structure at all, but rather an optical effect. This could involve the selective scattering of sunlight by particles possessing specific properties distributed in patterned arrangements around the object. Certain dust grain compositions exhibit a preferential scattering of light at particular wavelengths. If the 3 Atlas is ejecting different types of dust from distinct regions of its surface, and these dust types separate spatially as they move away from the nucleus, influenced by their size and composition, it could lead to the formation of distinct color zones. This phenomenon occurs to some extent in all comets. Heavier particles follow trajectories that deviate slightly from those of lighter particles. However, achieving the precise separation observed by Earth would demand an exceptionally organized ejection process. Each material type would need to originate from specific surface regions and maintain its distinctiveness as the coma expands. While challenging, this scenario is not physically impossible. Some comets display jets that exhibit distinct colors when imaged using narrow-band filters designed to isolate specific emission lines. What raises concern among careful observers is the confluence of these observations: color separation, geometric patterns, the enigmatic disappearances in LASCO images, trajectory anomalies, and the brightness paradox. Each individual element possesses plausible natural explanations that, while perhaps stretching the boundaries of conventional understanding, do not fundamentally violate the laws of physics. However, when considered collectively, these phenomena begin to appear less like a series of coincidences and more indicative of a system exhibiting behaviors that we are not yet adequately equipped to interpret. In the realm of SETI research, there is the well-known Drake equation. However, a lesser-known framework exists, termed the Rio scale. This scale is designed to quantify the significance of potential SETI detections, assigning a rank from 0, signifying readily identifiable natural or human-made interference, to 10, indicating unambiguous evidence of extraterrestrial technology. The scale takes into account factors such as the signal's distance from Earth, its information content, the possibility of independent verification, and how well it aligns with natural explanations versus artificial ones. The Object Through 2 Atlas does not fit neatly onto the Rio scale because it is not a signal but a physical entity. Nevertheless, if one were to apply a similar logical framework, the observed geometric plasma structures would likely fall into the intermediate range. They are not definitive proof, nor are they easily explained by standard models. Their verification would necessitate multiple observations from independent sources. While potentially natural under unusual but physically permissible conditions, the accumulation of evidence increasingly makes ignoring them more difficult than pursuing their investigation seriously. The observed plasma patterns also raise practical considerations regarding observation priorities. If these patterns represent genuine structural features within the coma, rather than artifacts or illusions, then high-resolution spectroscopic imaging becomes imperative. This would entail acquiring hyperspectral data cubes, which illustrate the spatial distribution of each emission line, rather than relying solely on single-wavelength photographs. Such data would immediately differentiate between organized plasma exhibiting sharp boundaries and complex optical effects arising from dust scattering. It would also reveal whether magnetic fields are implicated, whether electric currents are flowing through the coma, or if this object generates electromagnetic environments unlike any comet previously studied. Spacecraft observations conducted in early November might offer some of this crucial data. The spacecraft is equipped with spectrometers and particle detectors capable of characterizing the plasma environment, provided it can achieve sufficient proximity and precisely orient its instruments. However, the JUICE mission is primarily optimized for studying Jupiter's moons, not interstellar comets. Consequently, the observation window will be restricted, and the geometrical alignment might not be ideal for discerning fine spatial structures. Ground-based observations are set to continue after 3-thuned Atlas emerges from its solar conjunction. Amateur astronomers equipped with advanced instruments can capture images that depict the overall morphology of the coma. Professional observatories, utilizing adaptive optics and integral field spectrographs, can perform detailed analyses. The pivotal question remains whether these observed patterns are persistent or represent transient features specific to the object's state during October. If the geometric configurations dissipate, it would lend credence to the argument that they were indeed artifacts or temporary phenomena associated with the comet's perihelion passage. Conversely, if the patterns endure, and subsequent observations by multiple independent research groups consistently confirm structured light distribution with distinct color separation and geometric regularity, then we would be confronted with a genuine enigma demanding an explanation that transcends mere speculation about unusual conditions. Plasma physics provides the necessary tools for diagnosing such situations. It is possible to model the expected plasma behavior around a comet, incorporate solar wind parameters, estimate the magnetic field strengths required to produce the observed structures, and compare these requirements with those generated by known natural sources. If the analysis indicates that maintaining the observed geometry necessitates conditions that are implausible within a natural cometary environment, only two possibilities remain. Either our models of plasma physics are incomplete, or 3-3 Atlas is not solely governed by natural processes. The cross pattern, in particular, poses a quandary for physicists conversant with plasma confinement techniques. Fourfold symmetry is a characteristic feature of engineered magnetic traps, where coils are configured in a quadrupole arrangement. Nature rarely produces such precise symmetry without very specific external influences. Such symmetry is observed in crystals, where atomic lattices dictate their structure, and in certain planetary magnetospheres, where geometric effects resulting from rotation and solar wind interaction generate organized patterns. However, within a cometary coma, situated far from any rotating celestial body and possessing weak or non-existent internal magnetic fields, justifying a cross pattern through standard physics presents a significant challenge. Further insights are anticipated by December. By that time, the object will have moved sufficiently far from the Sun, mitigating the interference of solar glare in imaging attempts. The geometrical alignment will become more favorable for observatories located in the northern hemisphere. High-resolution photometry and spectroscopy will either confirm the reality and persistence of the plasma structures or demonstrate that they were merely observational artifacts specific to the challenging viewing conditions encountered in October. Regardless of the outcome, both possibilities hold significant scientific value. If they are artifacts, we will gain a deeper understanding of the limitations of our detection methodologies and the meticulous care required when interpreting images of faint celestial objects. If they are genuine, we will be compelled to confront a phenomenon that challenges our current comprehension of cometary behavior, or perhaps consider the profound possibility that 3-3 Atlas is not a comet at all. The phenomenon initially described as a jet flipping into an anti-tail has now evolved into a tail. Cometary tails are among the most iconic features in the astronomical sciences. They consistently point away from the Sun, perpetually elongated by solar wind and radiation pressure into vast streamers that can extend millions of kilometers into the void of space. The underlying physics is remarkably straightforward. Sunlight carries momentum. When photons interact with dust particles ejected from a comet, they transfer this momentum, propelling the particles away from the Sun. The solar wind, a continuous stream of charged particles emanating from the Sun at speeds of hundreds of kilometers per second, exerts a similar force on ionized gas. Both of these effects operate in the same direction, away from the source of radiation and wind, thereby creating the classic cometary tail. Occasionally, two tails are observed. A dust tail, which exhibits a slight curvature due to the greater mass of dust particles, making their orbital motion a relevant factor, and an ion tail, which is straight and often bluish, composed of ionized gas that responds primarily to the magnetic field of the solar wind. Both invariably point away from the Sun. This behavior is so fundamental to comets that it is one of the initial concepts introduced in introductory astronomy. Tails point away from the Sun, always, except when they don't. Anti-tails, more precisely termed anthelion tails or sunward spikes, are rare but documented phenomena where material appears to stream towards the Sun rather than away from it. The designation anti-tail is somewhat misleading, as it is typically an optical illusion. Perspective effects, when viewing the comet from specific angles, can create the visual impression that a portion of the tail is projecting forward. Imagine observing a curved structure almost edge-on. The segments of the curve that extend towards you may appear to point in the opposite direction to those extending away. Anthelian tails arise from viewing geometry, not from the actual sunward motion of the material. The 3 Atlas exhibited something different. The Hubble Space Telescope captured an image of the comet on July 21st, providing a high-resolution view of its coma and surrounding material. The image revealed a prominent sunward spike, with material extending from the nucleus in the direction of the sun. This was not a subtle perspective effect, but a clearly defined structure with an elongation of approximately 2:1 in the projected view. However, upon correcting for the viewing angle, Avi Loeb and Eric Quito calculated that the 3-dimensional elongation was approximately 10:1. This indicated the presence of a jet rather than an optical illusion. The physics governing the creation of a sunward jet is counterintuitive. It involves overcoming the forces of radiation pressure and solar wind, both of which act to push material away from the sun. The explanation proposed by Loeb and Cato in their September publication centers on the specific processes of ice sublimation. When carbon dioxide ice on the comet's surface absorbs solar radiation, it undergoes sublimation, transitioning directly from a solid to a gaseous state. This gas expands rapidly, carrying with it fragments of water ice that were either embedded within or resting upon the carbon dioxide ice. These ice particles, once detached from the surface, effectively scatter sunlight, generating the visible glow we perceive as a coma. However, these water ice particles also sublimate. At the temperatures relevant in this context, a few hundred Kelvin, water ice does not persist indefinitely. The ice particles themselves convert to gas over time, a process that takes minutes to hours depending on their size. If the sublimation process ejects ice particles with significant velocity, and these particles begin to sublimate immediately upon release, they form a stream of material that moves away from the nucleus but continuously loses mass. The critical factor is timing. At distances ranging from 3 to 4 astronomical units from the sun, the sublimation of water ice results in a peak in the scattering cross-section. The solar heating is sufficient to sublimate the particles rapidly, but not so intense that they vanish instantaneously. This delicate balance creates a region where the density of light-scattering ice particles reaches its maximum. If this region of maximum density happens to be situated sunward of the nucleus, it results in the formation of an anti-tail. The particles are emitted outward in all directions from the comet. However, those moving sunward persist for a longer duration before fully sublimating compared to those moving away from the sun. This asymmetry in particle lifetime leads to an apparent asymmetry in the brightness distribution. While still an optical effect to a degree, not representing true sunward motion, it is rooted in the real physics of how sublimation rates vary with heliocentric distance. This provides a natural explanation for what Hubble observed in July. The mathematical modeling supports this, with the model published by Loeb and Cato accurately fitting the observed elongation ratios and brightness distributions. Crucially, it also predicts a specific outcome. As 3 Atlas continues its trajectory towards the sun, moving from 4 astronomical units inward to 2, and eventually to its perihelion at 1.356 astronomical units, the sublimation rates are expected to change. Water ice particles ejected at closer distances will sublimate more rapidly, causing the peak scattering region to shift. Consequently, the anti-tail structure should diminish and eventually disappear, giving way to more symmetrical outgassing and potentially evolving into a traditional tail as refractory dust, which sublimes less readily, begins to dominate the coma. In September, New images obtained from the Nordic Optical Telescope in the Canary Islands corroborated this prediction. The anti-tail had indeed diminished. In its place, a faint tail extended away from the sun, a configuration consistent with normal cometary behavior. David Jewett and Jane Liu published their analysis in mid-October, documenting this transition with photometric measurements that illustrated the change in mass flow geometry. This sequence of events should have been conclusive. A prediction was made, tested, and confirmed. Natural cometary behavior, explained by well-established physics, rendered the anti-tail not evidence of propulsion or technological control, but a manifestation of sublimation physics unfolding precisely as theory suggested. The case appeared closed. However, Adam Hibbard, a colleague of Loeb's at Harvard, raised a disquieting question. He posited that if one were operating a spacecraft and intended to decelerate as it approached a star system, the standard procedure would be to fire the engines in the direction of travel, generating thrust that opposes the spacecraft's velocity. This maneuver is known as a retrograde burn in spacecraft terminology. The exhaust plume would stream ahead of the spacecraft, creating a visible trail pointing towards the destination. From the perspective of an external observer, this would precisely resemble an anti-tail, with material extending towards the sun, contrary to the expected direction. Subsequently, upon completing the braking maneuver and needing to adjust the trajectory for planetary encounters, the thrust orientation might be reversed, firing the engines in the opposite direction to provide acceleration or make course corrections. This exhaust would stream behind the spacecraft, generating a structure akin to a traditional tail. Again, from an observer's viewpoint, this would appear identical to the observed behavior of 33rd Atlas. An anti-tail was evident in July and August, followed by a transition period in September, and culminating in a normal tail by October. The timing of these events aligns disturbingly well. If 33rd Atlas were, in fact, a spacecraft executing a deceleration burn followed by perihelion maneuvering, the observed sequence of anti-tail to tail transition would unfold over precisely the timescale documented. The total amount of material expelled, estimated at approximately 2 million tons based on integrated production rate measurements, constitutes a mere 0.00005% of the celestial body's overall mass. This quantity, if spread uniformly across a sphere with a diameter of 5 kilometers, would form a surface layer roughly 4 centimeters in thickness. For a natural comet, an ablation of this magnitude is insignificant. Comets routinely shed meters of their outer material during close passes to the sun. Consequently, the volume lost provides negligible insight into the object's internal composition. However, for a spacecraft equipped with a protective shell designed to simulate cometary activity while safeguarding internal components from solar radiation, a 4-centimeter ablation layer is entirely plausible. This amount of material would be sufficient to generate convincing spectroscopic signatures and observable phenomena, yet not so substantial as to risk exposing the underlying structure. Lowe has candidly acknowledged that the natural explanation for the observed reversal of the jet's direction is entirely credible. The Kitto-Loeb model does not necessitate any extraordinary assumptions. It relies on standard thermodynamic principles and radiative transfer models. The rates of sublimation, the sizes of the ejected particles, and their light-scattering properties all fall within the typical ranges observed for cometary materials. Were these observations presented to the majority of planetary scientists without any mention of 3I Atlas's other peculiarities, they would likely conclude that the data is consistent with a comet transitioning from distant, cold activity, dominated by carbon dioxide, to warmer, closer activity, where refractory dust becomes a significant factor. The persistent issue is that these other anomalies do not simply vanish. The deviations in its trajectory, the paradox of its brightness, the geometric configurations of its plasma emissions, peculiar compositional characteristics such as the presence of nickel without iron, extreme negative polarization readings, its orbital alignment with the ecliptic plane, and the timing of its proximity to multiple planets all present challenges. While each of these individual phenomena can be explained by natural occurrences, each requires a distinct set of specialized conditions. The nickel anomaly, for instance, demands an unusual composition. The polarization requires atypical dust properties. The plasma geometry points to unusual magnetic fields. The brightness anomaly might be attributed to unusual viewing geometry. At a certain point, relying on a multitude of independent, improbable natural conditions becomes less scientifically economical than proposing a single unifying explanation that accounts for all observed characteristics. If 3I Atlas is indeed a manufactured object, an artificial probe or spacecraft, rather than a natural comet, then all of the observed anomalies can be readily understood as expected behaviors for an engineered system operating within an environment for which it was not originally designed. Its composition would reflect manufacturing processes rather than natural celestial formation. Its trajectory would be indicative of deliberate navigation rather than passive gravitational influence. Its brightness management would align with operational priorities such as power generation or thermal regulation, rather than a simple thermodynamic response to solar heating. The orientations of its jets would suggest the operation of a propulsion system rather than asymmetric sublimation. This is precisely the hypothesis that Adam Hibbert meticulously explored in his analysis. He is not asserting definitively that the object is artificial, but rather highlighting that the artificial hypothesis effectively eliminates the need to invoke numerous stacked coincidences. Occam's razor, the principle that favors simpler explanations, typically guides us towards natural interpretations. A rock is generally considered more probable than a spacecraft. However, Occam's razor also mandates minimizing the number of independent assumptions. In this context, positing one highly unconventional assumption, that the object is technological, versus 7 or 8 distinct, unusual natural conditions, significantly alters the calculation of parsimony. The observations scheduled to occur after its perihelion passage will provide a direct test of these competing hypotheses. If 3I Atlas is a natural phenomenon, it should continue to exhibit cometary evolution. Its tail should grow brighter as solar heating exposes fresh material. Spectroscopic signatures should remain consistent with the composition of an icy body. Its activity should gradually diminish as it recedes from the sun and its temperature drops. All of these predictable outcomes are governed by thermodynamic principles. Conversely, if the object is artificial and the observed anti-tail was indeed the result of a deceleration burn, its post-perihelion behavior might differ. Its activity could decline more abruptly than anticipated if its propulsion system is deactivated after completing its navigational maneuvers. Its spectroscopic signatures might change if the surface coating is depleted, revealing underlying materials. Its brightness might stabilize at levels inconsistent with the continued sublimation of ice. Any of these scenarios would be exceedingly difficult to reconcile with conventional cometary models. Furthermore, there exists the possibility of secondary deployments. If the object is a mothership, as Lowe has speculated, then perihelion would be the opportune moment to release smaller probes, mini spacecraft engineered to intercept planets, asteroids, or other points of interest. Such deployments would manifest in photometric data as sudden shifts in brightness, or in astrometric measurements as the appearance of multiple distinct light sources where previously only one was detected. The high-cadence monitoring planned for November and December is specifically designed to detect these potential signatures. The observed reversal of the jet itself is not conclusive proof of anything. It is consistent with natural cometary behavior, but it is also compatible with spacecraft propulsion. The fact that both explanations remain viable underscores the necessity for additional data to differentiate between them. The critical observations are anticipated within the coming weeks. Will the tail's behavior continue to conform to natural sublimation models? Will the object's trajectory remain purely gravitational, or will it exhibit further deviations? Is there any evidence of fragments or secondary objects separating from the main body? Avi Loeb has publicly stated that if 3I Atlas behaves in a manner consistent with natural processes through its perihelion passage and subsequent observations, he will reclassify it on his observational scale to a rating of 2, signifying an object that is unusual but likely natural. The anomalies would still be considered noteworthy and worthy of study, but would not be interpreted as indicative of technology. However, if the post-perihelion data reveals anything inconsistent with natural evolution, if the object persists in systematically defying standard cometary models, then the hypothesis of it being technological will become significantly more challenging to disregard. We are witnessing a test unfolding in real time. Nature has presented us with an interstellar visitor exhibiting enough peculiarities to prompt questions, but not enough definitive evidence to compel conclusions. The observed reversal of the jet, the transition from an anti-tail to a tail, is one component of this complex puzzle. When examined in isolation, it is unremarkable. However, when considered within the broader context of all that 3I Atlas has revealed, it becomes yet another data point in a pattern that stubbornly resists resolution into a comfortably familiar pattern. By mid-December, when the object reaches its closest approach to Earth, we will have amassed months of post-perihelion observational data. The tail's behavior will be thoroughly documented, its trajectory precisely measured, and its spectroscopic evolution meticulously tracked. Either all of this accumulated data will converge to support natural cometary explanations, or it will not. If it does not, and if 3I Atlas continues to exhibit systematic peculiarities that align with engineered behavior, then the discourse will shift from whether the technological hypothesis warrants consideration to how we should respond to it. IAON Planetary Defense Activation. The International Asteroid Warning Network does not issue pronouncements lightly. Established under the auspices of United Nations coordination in 2013, IAWN's sole purpose is to detect, track, and characterize objects that may pose collision risks to Earth, including near-Earth asteroids and comets on intersecting orbits. Anything with even a remote possibility of impact is flagged, analyzed, and monitored until its trajectory is fully understood. This represents a global collaborative effort involving space agencies, observatories, and research institutions spanning dozens of nations. When IAWN issues a campaign notice, it signifies that a particular object has triggered their threat assessment protocols. On October 21, 2025, the same day that 3I Atlas entered solar conjunction, IAWN released an official notice through the Minor Planet Center. This announcement declared a coordinated observation campaign targeting 3I Atlas, scheduled to run from November 27th through January 27th, 2026. This marks the inaugural instance in IAWN's history where an interstellar object has been designated for a planetary defense campaign. Consider that statement carefully. Planetary defense, not merely scientific curiosity or routine monitoring of an intriguing visitor. Defense. The language employed in the announcement adopts a diplomatic tone, describing the campaign as an exercise to enhance astrometric techniques for challenging targets such as comets exhibiting extended comas and complex morphologies. They present it as a training opportunity, a chance for the global observing community to hone their skills in extracting accurate positional measurements from difficult-to-observe objects. However, the underlying implication is unmistakable. IAON does not typically organize 2-month campaigns for objects that pose no threat whatsoever. 3I Atlas is projected to pass Earth at a distance of 1.8 astronomical units, equivalent to approximately 269 million kilometers. This distance is roughly 700 times farther than the Moon. There is no risk of collision. Absolutely none. The object's trajectory is hyperbolic, meaning it is not gravitationally bound to the sun. It is merely passing through and will depart. So, why is the Planetary Defense Network mobilizing resources typically reserved for potentially hazardous asteroids? The announcement did cite specific technical challenges. Comets indeed present unique difficulties for astrometry because their comas and tails can displace the apparent center of the object from the actual nucleus position. When determining a comet's location, astronomers are effectively measuring the center of its brightness, which can be offset from the physical nucleus by thousands of kilometers if the outgassing is asymmetrical. This introduces errors into trajectory predictions. This is a legitimate concern for comet tracking. However, IAWN has never before initiated a campaign to address this particular issue. They have successfully tracked hundreds of comets over the years without requiring coordinated international efforts to refine measurement techniques. The timing of the campaign is also significant. It commences on November 27th, precisely 1 month after perihelion. This period is optimal for observation, as 3I Atlas will be sufficiently distant from the Sun for clear viewing, yet still close enough to Earth that parallax measurements from various locations will provide a robust baseline for distance determination. The campaign concludes on January 27th, allowing for a full 2 months of intensive tracking as the object recedes from the inner solar system. This 2-month period of coordinated observation, involving dozens of facilities worldwide, is focused on an object that poses no collision threat. IAWN's announcement also contains another unusual stipulation. Participation requires registration and attendance at a workshop. Individuals wishing to join the campaign must register by November 7th and attend a technical workshop on comet astrometry techniques. Only participants who successfully complete this workshop will be eligible to contribute observations to the official dataset. This level of participant vetting is unprecedented for IAWN campaigns. Typically, they welcome data from any qualified observer, recognizing that more observing telescopes lead to more accurate trajectory solutions. Restricting participation suggests a desire for stringent control over who contributes data and how that data is analyzed. 3 days prior to IAWN's announcement, on September 30th, Avi Low submitted a white paper to the United Nations in collaboration with his colleagues Omar Eldadi and Gershon Tenenbaum. This paper, titled Advancing Interstellar Science, advocated precisely for what IAWN is now undertaking: coordinated global observation of interstellar objects to maximize coverage and ensure optimal scientific monitoring. Low's argument in the white paper is direct. If interstellar visitors could potentially carry alien technology, even with a low probability, the implications for humanity are significant enough that such objects should be treated with the same level of seriousness as potential impact threats. The white paper references black swan events, situations characterized by low probability but immense consequences. While standard risk assessment methodologies might dismiss low probability scenarios, the potential outcomes in this case, such as first contact with extraterrestrial intelligence, or, more concerningly, hostile technology entering our planetary system, fundamentally alter probability calculations. In such circumstances, one does not wait for certainty. One acts on precaution. IAWN's campaign, launched less than a month after that white paper reached UN committees, suggests that the argument was taken seriously. This creates an interesting dichotomy. Publicly, space agencies maintain that 3I Atlas is a natural comet exhibiting unusual but explicable characteristics. NASA's official statements emphasize that there is no threat to Earth and that the object will pass safely through the solar system. Tom Statler, NASA's lead scientist for small bodies, has officially stated that all available data points towards a cometary classification. The European Space Agency echoes this position, asserting that all is routine and there is nothing to be concerned about. However, beneath this public pronouncement, IAWN, an organization supported by the United Nations and specifically tasked with planetary defense, is orchestrating the most comprehensive observation campaign ever directed at an interstellar object. They are doing so during the precise temporal window when any unexpected behavior from the object would likely become apparent. They are limiting participation to vetted observers who have undergone specialized training. Furthermore, they are coordinating with international space agencies to ensure global coverage, meaning that regardless of where 3I Atlas appears in the sky, multiple facilities will be tracking it simultaneously. The disparity between public messaging and institutional action is stark. If 3I Atlas is merely an intriguing but harmless comet, why mobilize planetary defense resources? If there is even a slight concern that it might be something else, why publicly downplay that possibility while intensifying monitoring efforts privately? One plausible explanation is institutional caution, devoid of outright alarm. Space agencies have learned from past communication failures that premature announcements can incite public panic that is disproportionate to the actual risk. Recall the case of asteroid Apophis, discovered in 2004, with initial impact probability calculations indicating a small but non-zero chance of collision with Earth in 2029. Media coverage generated widespread anxiety before refined observations definitively showed the impact risk to be essentially nil. Agencies are keen to avoid repeating such a pattern. It is deemed preferable to conduct intensive monitoring, gather conclusive data, and then issue public statements only when conclusions are certain. However, this explanation assumes the risk is related to impact. 3I Atlas will not strike Earth. Its trajectory is unambiguous on this point. So, what risk is IAWN concerned about? The campaign announcement does not explicitly state it. It alludes to improving astrometric techniques and highlights the scientific value of studying rare interstellar visitors, framing the entire endeavor as an opportunity rather than a threat. Yet, the structure of the campaign, the resources being deployed, and the level of coordination all suggest that this is being treated as more than mere scientific curiosity. Lowe's white paper offers a potential rationale that official channels are reluctant to articulate. If 3I Atlas releases secondary objects at perihelion, numerous probes or fragments detaching from the main body, these secondaries could be on trajectories that bring them closer to Earth than the primary object. Detecting and tracking such secondaries necessitates coordinated observation with high-cadence monitoring. Multiple facilities must be observing simultaneously so that if an object separates, it is documented immediately and tracked continuously until its trajectory is fully characterized. The IAWN campaign is meticulously designed for precisely this scenario. 2 months of intensive monitoring, numerous observation sites providing redundant coverage, standardized measurement techniques ensuring comparability of all positional data, and workshop training to equip observers with the skills to distinguish genuine objects from artifacts or noise. It is, in essence, a deployment protocol for detecting and tracking unexpected secondary objects. Another aspect rarely discussed publicly is the potential for trajectory alterations post-perihelion. If 3I Atlas executes maneuvers during its obscured passage behind the Sun, these maneuvers could potentially redirect it towards a closer Earth approach than currently predicted. While the probability of this occurring is low, when conducting threat assessments, one cannot disregard low probability scenarios with high consequence outcomes. Intensive tracking of the object immediately following perihelion allows for the detection of trajectory changes within days rather than weeks, thereby maximizing warning time if the approach distance begins to decrease. IAWN's involvement also signals something about internal discussions at governmental levels. The organization reports to the United Nations Committee on the Peaceful Uses of Outer Space. For this committee to approve and allocate resources for this campaign, it would have required briefings, presentations, and a consensus among member states that such monitoring is justified. Whatever data or analysis has convinced those committees remains undisclosed to the public. We observe the output, the campaign itself, but not the input, the evidence or arguments that motivated the decision. There is precedent for this kind of monitoring. When asteroid 2012 TC4 made a close approach to Earth in October 2017, passing within 44,000 kilometers, IAWN coordinated an observation campaign. That campaign had a clear objective. The asteroid had been recently discovered with an uncertain trajectory. Close approaches provide excellent opportunities to refine orbital parameters and assess future collision risk. It was conceivable that 2012 TC4 might return in the future on a more threatening path. Therefore, gathering data during the 2017 passage was operationally valuable. 3I Atlas, however, is different. It is not returning. Its hyperbolic trajectory indicates this is a singular passage through our solar system. After it departs the inner solar system in early 2026, it will never return. 50,000 years from now, it will be light years distant, traversing interstellar space towards an unknown destination. Thus, the IAWN campaign is not focused on future threat assessment. Rather, it is dedicated to understanding the events transpiring during this unique passage through our cosmic neighborhood. The workshop requirement introduces an additional layer of complexity. What specific techniques are being taught? Standard astrometry is a well-established discipline. Measuring the positions of comets is not fundamentally different from measuring the positions of asteroids. One accounts for the extended coma by fitting models to the brightness distribution and subsequently determining the nucleus's position. This is considered routine work. What specific training do observers require that is not already standard practice? One possibility is training in detecting faint companions. If secondaries detach from 3I Atlas, they will be considerably dimmer than the primary object. Standard cometary observation techniques are optimized for the bright central region. Detecting faint, nearby objects necessitates different processing methods, distinct exposure times, and alternative analysis techniques. The workshop may be intended to instruct observers in these specialized techniques, preparing them to identify objects that would not typically be visible in standard cometary imagery. Another potential reason is the establishment of rapid response protocols. If an unexpected phenomenon occurs, IAWN requires immediate notification rather than delayed reporting through conventional scientific channels. The workshop could therefore serve to establish communication procedures outlining whom to contact, what information to include, and how to format the data. Building this communication network prior to the campaign's commencement ensures that if a noteworthy event transpires, the response is coordinated rather than chaotic. The campaign also serves a diplomatic purpose. By engaging observatories from numerous countries, IAWN ensures that the resulting data is not monopolized by a single nation or agency. Should discoveries be made, they will be inherently international, shared among all participating entities. This approach mitigates scenarios where one country might claim exclusive control over information pertaining to something of potentially significant consequence. It embodies transparency through collaboration, ensuring that no single entity can claim proprietary knowledge or conceal important findings. For the general public, IAWN's campaign conveys a mixed message. On one hand, it is reassuring to know that serious institutions are diligently monitoring 3I Atlas. If there were genuine concerns about a threat, having planetary defense systems engaged and actively observing would be the desired outcome. On the other hand, the very fact that these systems are engaged raises questions about the underlying reasons for their involvement. What could possibly warrant such intense scrutiny? The explanation is likely far less sensational than speculative narratives suggest. Object 3I Atlas presents a genuinely peculiar profile. The confluence of its unusual characteristics, regardless of their ultimate cause, certainly justifies careful observation. The International Astronomical Union's IAU initiative to practice coordinated surveillance makes perfect operational sense. Should a genuine threat materialize in the future, having internationally trained teams experienced in rapid, large-scale operational deployment will prove invaluable. Object 3I Atlas, whether inherently dangerous or not, serves as an ideal training exercise. However, training drills are typically publicly declared as such. The specific terminology employed by the IAU, the operational structure of the surveillance effort, and the limitations placed on participation all strongly imply this is more than a mere drill. This is operational. They are treating 3I Atlas as an entity requiring active monitoring under protocols normally reserved for objects of significant concern. November 27th marks the official commencement of the surveillance campaign. Between now and then, 3I Atlas will complete its closest approach to the Sun, re-emerge from behind the Sun's glare, and once again become visible. The initial observations of the campaign will document the object's condition following its perihelion passage. This foundational data set will then serve as the benchmark for all subsequent analysis. Should the object exhibit deviations from its pre-perihelion observations, differences in luminosity, spectral signature, physical form, or orbital path, these changes will be immediately apparent in the campaign data. The IAU is deploying dozens of telescopes to observe this reappearance. They are meticulously coordinating observation schedules to ensure uninterrupted coverage. Observers are being trained to identify specific indicators that might suggest phenomena beyond typical cometary behavior. Crucially, all of this is being undertaken within the framework of planetary defense, language that implies they deem 3I Atlas relevant to Earth's safety, despite its trajectory posing no immediate impact risk. The extent of their prescient knowledge remains elusive. However, what they might suspect, but are unwilling to disclose publicly, is more readily inferred, and what they will uncover as intensive monitoring commences in late November might finally provide an answer to the question that has grown increasingly pressing since July. Are we witnessing the most extraordinary comet in recorded history? Or something else entirely? The connection to the WOW signal. On August 15th, 1977, the Big Ear radio telescope at Ohio State University was conducting its routine celestial survey, searching for discernible patterns in radio emissions that might indicate intelligence beyond natural cosmic background noise. The telescope was not focused on any particular type of signal. It was part of a broader endeavor in the search for extraterrestrial intelligence, SETI, systematically scanning radio frequencies with the hope that a signal might emanate from somewhere in the cosmos. At 10:16 p.m. Eastern Time, the telescope registered a signal at 1,420 megahertz. This frequency falls precisely within the band of the hydrogen line, a radio emission originating from neutral hydrogen atoms abundant throughout the galaxy. It is considered an optimal choice for interstellar communication, given that hydrogen is the universe's most prevalent element, a fact that any technologically advanced civilization would undoubtedly recognize. The signal persisted for 72 seconds, precisely the duration it takes for Big Ear's observational beam to sweep across a fixed point in the sky as the Earth rotates. Jerry Amon, reviewing the computer printouts several days later, noticed a significant intensity spike. The signal's strength far exceeded that of the ambient background noise, making it immediately conspicuous. He encircled the alphanumeric sequence 6EQUJ5 and annotated the margin with the word WOW. This annotation ultimately gave the signal its enduring name, the WOW signal. Almost 50 years later, it remains one of the most captivating detections in SETI's history. No definitive explanation has ever fully accounted for it. Despite decades of subsequent observational efforts, no further detections of this signal have ever been made. The origin of the signal was traced to a specific region within the constellation Sagittarius. Its coordinates were identified as a right ascension of 19 hours 25 minutes and a declination of 27 degrees. These coordinates do not pinpoint a singular celestial body, but rather indicate a direction. Observing these coordinates directs one's gaze toward the galactic center of the Milky Way, passing through dense stellar fields and molecular clouds that obstruct a clear view of the core. Tens of thousands of stars reside within the observational cone of Big Ear's antenna when directed at that location. Precisely identifying which star, if any, was the source of the signals is impossible without additional detections. Fast forward to the year 2025, Object 3I Atlas makes its appearance within our solar system, marking the third confirmed interstellar visitor we have ever detected. Its trajectory, when traced backward through space, originates from the Sagittarius region. While not precisely the same coordinates as the WOW signal, such exactitude would be too convenient. It falls within a 9-degree arc on the celestial sphere. A 9-degree angular separation represents a substantial area when considering interstellar distances. However, directionally, it is remarkably close. This proximity is significant enough that Dr. Avi Loeb calculated the probability of such a random alignment occurring at approximately 0.6%. This figure is noteworthy. 0.6%, while not an impossibly low chance, is uncommon enough that when combined with the other statistical anomalies associated with 3I Atlas, the cumulative probability diminishes to ranges where attributing it to randomness becomes increasingly difficult to sustain. Multiplying 0.6% by the 0.2% chance of ecliptic alignment, then by the 0.005% chance of opportune planetary encounter timing, and subsequently by the various anomalies related to its composition and observed behavior, one rapidly arrives at probabilities measured in parts per quadrillion. Dr. Loeb's analysis extends further. If the WOW signal indeed originated from 3I Atlas back in 1977, what conditions would have been necessary? Firstly, distance. Where was the object in 1977? Tracing its trajectory backward at a velocity of 58 kilometers per second, while accounting for the gravitational influences of the Sun and planets, places it approximately 600 astronomical units from Earth in August of 1977. This distance is roughly 90 billion kilometers, situated deep within the outer solar system beyond the Kuiper Belt, yet still technically within the Sun's gravitational dominion. At such a vast distance, transmitting a signal detectable by Big Ear would have required between 0.5 gigawatt and 2 gigawatts of power, depending on antenna gain and beam focus. This power output is comparable to a large nuclear power plant on Earth. While not an insurmountable feat for an advanced civilization, it is certainly not trivial. Such power levels are not broadcast casually unless there is a compelling reason. The signal also exhibited a blue shift of approximately 10 kilometers per second, indicating the source was moving toward Earth. Object 3I Atlas is currently moving toward the Sun, and by extension, was moving in Earth's general direction back in 1977. The Doppler shift is consistent, though not perfectly matching, as precisely measuring velocities from a single 72-second signal is inherently challenging. However, it falls within acceptable uncertainty ranges. This is where the speculation becomes both captivating and perplexing. If 3I Atlas transmitted the WOW signal, for what purpose? Dr. Loeb posits it might have been a radar pulse rather than a communication attempt, an active sensor sweep designed to detect planetary bodies within the inner solar system. When approaching a star system from interstellar space, understanding the locations of planets is operationally crucial. They are imperceptible optically from hundreds of astronomical units away, too dim and lost in the glare of stars. However, by transmitting a powerful radar pulse and analyzing the reflections, one can detect substantial bodies and characterize their orbits. Earth would have reflected a minuscule portion of that pulse. Venus would have returned a detectable signal. Jupiter, despite its greater distance from the transmission point in 1977, would have yielded a more significant reflection due to its immense size. By meticulously analyzing the timing and intensity of these reflections, provided one is patient enough to await the round-trip travel time of the signals, one could effectively map the architecture of the inner solar system. This would enable precise targeting for trajectory adjustments for optimal planetary encounters decades later, upon arrival. The primary challenge with this hypothesis lies in verification. We possess a single detection, a solitary 72-second signal that has never been replicated. Radio SETI efforts have repeatedly directed telescopes toward that region of Sagittarius over the decades. Modern instruments, significantly more sensitive than Big Ear, have scanned across broader frequency ranges and employed longer integration times, yielding nothing. The WOW signal remains an anomaly, a singular event devoid of follow-up, confirmation, or supplementary data. This uniqueness could either suggest the signal was not a genuine extraterrestrial communication, or, conversely, that it was a targeted transmission not intended for repetition. If the purpose was to map a solar system via radar, a single pulse would suffice, followed by continued transit. Continuous transmission would represent an inefficient use of energy. This argument can be interpreted in two ways. Skeptics contend that the absence of repetition points to an instrumental error, terrestrial interference, or some transient natural phenomenon. Proponents argue that directed transmissions would not necessarily be repeated, and expecting them to be so reflects an anthropocentric bias based on our own radio astronomy practices. The arrival of 3I Atlas from approximately the same direction 48 years later lends credence to the radar hypothesis, though it does not definitively prove it. Coincidences do occur. Sagittarius is an exceptionally rich region of the sky. It hosts the galactic center, exhibits the highest stellar density from our perspective, and contains dense molecular clouds and stellar nurseries that generate complex radio backgrounds. An interstellar object originating from that direction and a mysterious radio signal emanating from the same region could be entirely unrelated. However, the temporal alignment is unsettling. If 3I Atlas departed its home system several million years ago, a duration likely given the vast distances and velocities involved, it would have been progressively approaching our solar system throughout the era of modern human civilization. The specific period when it was 600 astronomical units away, during the 1970s, coincides precisely with humanity's nascent serious endeavors in radio SETI. We began actively listening, just as a hypothetical probe would have been sufficiently close to warrant radar scanning of the inner system. This synchronicity troubles many observers. It suggests either the most remarkable coincidence in SETI history or a deliberate, non-coincidental alignment. If it is not a coincidence, the implication is that an entity had been approaching our solar system for millennia, and precisely at the juncture when it neared a distance conducive to active sensing, we coincidentally developed the technological capacity to detect such transmissions. The statistical probability of such an eventuality appears vanishingly small, unless there exists an interconnected causal relationship that we have yet to identify. One potential resolution suggests that the timing is not, in fact, remarkable. Human radio technology has only existed for approximately a century. Radio SETI, in particular, has been operational for perhaps 60 years. If interstellar probes are a common occurrence, regularly approaching solar systems across the galaxy, then the probability of one arriving during humanity's brief window of radio capability is not astronomically minuscule. It is merely rare on human timescales. We perceive it as significant because we are the ones experiencing it directly, but from a cosmic perspective, it may be unremarkable. Another possibility involves observer selection effects. Our ability to detect signals is inherently limited to the periods during which we are actively listening. If probes are continuously approaching solar systems, but only transmit when within specific proximity thresholds. We would only ever detect them if our listening period happened to coincide with that critical approach window. The vast majority of probes would likely go undetected, either arriving before we developed radio astronomy or departing after our civilization's demise. Those that we do detect are necessarily correlated with our technological capabilities. These anthropic arguments effectively neutralize the perceived coincidence without necessitating conspiracy or intentionality. While philosophically satisfying, they do not substantially advance our understanding of 3I Atlas's nature or the significance of the WOW signal connection. What would imbue the connection with tangible meaning is the detection of new transmissions. If 3I Atlas were to emit radio signals during its passage through the inner solar system, signals that we could detect and analyze, this would transform the current hypothesis from mere speculation into a verifiable scientific inquiry. To date, no radio telescope has reported the detection of transmissions emanating from 3I Atlas. This is not surprising if it is, in fact, a comet. Comets are generally radio quiet, producing only very faint emissions from their comas that necessitate highly sensitive instruments for detection. However, there is a critical gap. Major radio observatories have not been systematically monitoring 3I Atlas. SETI programs typically do not direct their instruments toward comets. Why would they? Comets are natural celestial bodies. SETI telescopes are aimed at stars, planetary systems, and regions of space where technological civilizations are deemed plausible, not at icy bodies traversing our own solar system. Dr. Loeb has advocated for dedicated radio observations of 3I Atlas, arguing that the accumulation of anomalies warrants its consideration as a SETI target, irrespective of how improbable the technological hypothesis might seem. The proposal is to point a dish antenna and listen across the hydrogen line frequency and adjacent bands to ascertain if any signal emerges beyond the background noise. The cost associated with such an observation is minimal, requiring only a few hours of telescope time. The potential reward, should a signal be detected, is immense. Yet, as of late October, no major facility has publicly announced plans to conduct such observations. A portion of this reluctance stems from institutional conservatism. SETI operates with limited budgets and engages in competitive proposal processes for telescope time. Directing resources toward 3I Atlas implies diverting them from more conventional targets that possess a stronger theoretical basis for potentially yielding detectable signals. If the observation yields nothing, which is the statistically expected outcome, it represents telescope time expended with zero scientific return. Proposal reviewers are understandably hesitant to approve what appears to be a long shot. However, there is also a more subtle consideration. If a radio telescope were pointed at 3I Atlas and a signal were detected, it would immediately create a profound dilemma. First contact protocols mandate rigorous verification, international collaboration, and meticulous analysis prior to any public announcement. The individual or team making such a discovery would then bear the responsibility for managing what could potentially be the most consequential observation in human history. Most scientists would prefer to avoid such a high-stakes position, particularly when the probability of success seems low. Consequently, we are left with a tantalizing potential connection that remains unconfirmed or unrefuted due to a lack of observations that no one is currently undertaking. The WOW signal occurred. Object 3I Atlas is arriving from approximately the same celestial direction 48 years later. The mathematical calculations for a radar transmission originating from the object's 1977 position are consistent. The Doppler shift aligns. The timing of active sensing relative to its arrival in the inner solar system corresponds with expectations for a mission profile designed for planetary system exploration. However, in the absence of new detections, this remains circumstantial evidence, suggestive but not conclusive. It is a pattern that could be imbued with profound meaning, or could be a manifestation of the human tendency to perceive meaningful patterns in random data, a phenomenon known as apophenia. We discern faces in clouds, construct constellations from disparate star arrangements, and identify causal links between events separated by decades because our brains are wired to seek causation even when only correlation exists. The scientific imperative is to acquire more data. This involves monitoring 3I Atlas with radio telescopes, analyzing its trajectory for any deviations that might indicate deliberate navigation toward Earth's orbit or planned planetary encounters. It also entails searching for secondary signals, transmissions that could occur as it passes perihelion or approaches Earth in December. Everything must be meticulously documented, allowing the evidence to accumulate until patterns either resolve into clear, natural explanations or into something that compels us to reevaluate our fundamental understanding of what we are observing. The months of November and December will be pivotal in this regard. As the object becomes readily observable again following its perihelion passage, any research group with access to radio telescope time could, in principle, conduct the necessary observations. Whether they will do so is contingent upon funding availability, the successful approval of proposals, and a willingness to allocate resources to what is largely considered a low probability target. However, the window of opportunity is limited. By February, 3I Atlas will be receding into the outer solar system, diminishing in visibility, and the chance to directly test the WOW signal hypothesis will be lost. If transmissions are detected, the entire paradigm shifts. The discourse will move from questioning whether 3I Atlas is unusual to addressing the implications of confirmed intelligent technology operating within our solar system. If no transmissions are detected, the connection will persist as a speculative curiosity, an intriguing coincidence that fuels academic papers and debates, but does not fundamentally alter our cosmological perspective. Regardless of the outcome, the WOW signal serves as a potent reminder that the universe has already presented us with an unexplained phenomenon that bears a striking resemblance to extraterrestrial contact. Object 3I Atlas's arrival from the same direction decades later could be mere coincidence. Alternatively, it might represent an opportunity for the universe to allow us to connect disparate pieces of information, revealing a pattern that spans nearly half a century and offers profound insights into our place within the cosmos. All that is required is a willingness to look. The 8 anomalies associated with 3I Atlas rank 4 on the scale. Dr. Avi Loeb developed this specific scale for interstellar objects precisely because 3I Atlas necessitated it. Prior to this object's appearance, such a framework did not exist. There was no standardized methodology for quantifying the degree of unusualness of an interstellar visitor, nor a metric for assessing the likelihood of a technological origin. Dr. Loeb devised a 10-point scale where 0 signifies a definitively natural origin, 10 signifies a definitively artificial origin, and the intermediate ranges capture varying degrees of anomalous characteristics and uncertainty. Currently, 3I Atlas is ranked at a 4. This rating is not based on conjecture or intuition, but on a calculated assessment derived from 8 distinct anomalies. Each of these anomalies has been assigned a probability of occurring through natural processes. Multiplying these probabilities together yields a cumulative likelihood that measures how expected or unexpected the object's characteristics would be if it had formed through natural means. The resulting figure places it firmly within the zone of uncertainty, too peculiar to be dismissed as ordinary, yet not definitively artificial. The first anomaly pertains to trajectory alignment. Object 3I Atlas approaches the Sun on an orbital plane inclined by a mere 5 degrees from the ecliptic. The ecliptic is not a physical structure, but rather the plane defined by Earth's orbit, and by extension, the approximate plane in which most solar system planets orbit. Its existence is a consequence of the solar system's formation from a rotating disk of gas and dust, where the conservation of angular momentum caused celestial bodies to orbit in roughly the same plane. Interstellar objects, however, have no inherent connection to this plane. They originate in other stellar systems with their own unique orientations. Upon ejection into interstellar space, their trajectories become randomized through gravitational interactions. Some may follow a prograde path, aligning with their parent system's rotation, while others may follow a retrograde path. Inclinations can span the entire spectrum from 0 to 90 degrees, with no discernible preference for any particular value. For 3I Atlas to arrive aligned within 5 degrees of our ecliptic purely by chance requires a highly specific geometric configuration. Of all possible approach vectors from interstellar space, only approximately 2% align this closely. While not impossible, representing a 2 in 100 chance, it constitutes the first statistical deviation from the norm. If one were designing a mission to efficiently explore a planetary system, selecting a trajectory within the ecliptic plane is advantageous, as reaching planets from this plane necessitates minimal fuel expenditure. Initiating a trajectory from a high inclination requires costly plane change maneuvers. The 5-degree alignment is optimal for access, yet suspicious for a natural arrival. The second anomaly concerns the timing of planetary encounters. Object 3I Atlas passes within tens of millions of kilometers of Mars in early October, then Venus in early November, and is projected to pass Jupiter in March of 2026. Close approaches to multiple planets during a single transit are uncommon. Most interstellar objects either pass by all celestial bodies without incident or encounter a single body by chance. The probability of arriving at precisely the opportune moment to pass in proximity to 3 major planets is approximately 0.005%, or 5 in 100,000. Again, while not impossible, when combined with the trajectory alignment, it means 2 unusual conditions are occurring concurrently. The product of 2% and 0.005% is 0.01%, or 1 in 10,000. We are entering the realm of lottery-like odds, and we have only accounted for 2 anomalies. The third anomaly is mass. The celestial body designated 3I Atlas dwarfs its predecessors in the realm of interstellar visitors. Oumuamua, first observed in 2017, was estimated to be a few hundred meters in diameter, weighing tens of thousands of tons. Boris, the second visitor in 2019, was marginally larger, but its mass was still in the low millions of tons. In stark contrast, 3I Atlas possesses a minimum diameter of 5 kilometers and a mass exceeding 33 billion tons, outclassing both prior visitors by factors ranging from the thousands to the millions. Furthermore, it travels at a significantly higher velocity. Oumuamua entered our solar system with a hyperbolic excess velocity of approximately 26 kilometers per second. Boris arrived at 32 kilometers per second. 3I Atlas, however, enters at a remarkable 58 kilometers per second. This combination of immense mass and elevated speed imbues it with a magnitude of kinetic energy far beyond that of its predecessors. Such a confluence of extreme mass and high velocity is an infrequent occurrence. Most substantial interstellar objects are gravitationally tethered to their parent stars. Only exceptionally rare ejection events can propel massive objects to such high velocities. The likelihood of detecting such an object during the brief technological window when humanity can identify interstellar visitors is exceedingly small, well below 1%. The fourth peculiarity lies in its composition, specifically the observed nickel emissions. Spectroscopic analysis conducted by the KEK Observatory in August revealed prominent nickel emission lines, conspicuously absent of corresponding iron lines. This ratio deviates significantly from what is expected for natural celestial bodies. Nickel and iron are intrinsically linked elements, forged together during stellar nucleosynthesis and typically found in similar proportions throughout the universe. Rocky bodies, asteroids, and comets alike exhibit iron in conjunction with nickel when subjected to spectral analysis. Industrially, on Earth, nickel alloys are deliberately manufactured to concentrate nickel while minimizing iron due to the superior properties of such alloys. Stainless steel, high-performance alloys for jet engines, and corrosion-resistant materials frequently employ compositions rich in nickel and low in iron. Discovering such a signature within a comet is akin to finding refined aluminum within a meteorite. While technically conceivable through extremely rare natural processes involving significant chemical fractionation, the probability of such an event is negligible, falling below 1%. The fifth anomaly pertains to its water content. Measurements obtained by the James Webb Space Telescope indicated that 3I Atlas has a mere 4% water by mass in its outgassing material. The majority of comets are primarily composed of water ice, with lesser quantities of carbon dioxide, carbon monoxide, and other volatile compounds. Comets within our solar system typically exhibit water comprising 70 to 90% of their outgassing. Even accounting for variations in composition and differing formation environments, a 4% water content is extraordinarily low. Instead, carbon dioxide dominates, constituting 87% of the observed volatiles. This inverted ratio suggests either the object originated in an exceptionally frigid environment where carbon dioxide ice is more abundant than water ice, or the observed surface has been depleted of water while retaining carbon dioxide. Both scenarios are plausible, but necessitate specific environmental conditions. While the precise probability of encountering an interstellar comet with such an unusual composition is difficult to quantify, it is estimated to be under 5%. The sixth anomaly involves polarization. Observations made by the Very Large Telescope in September revealed extreme negative polarization. This implies that light scattered from the comet's coma had its wave orientation parallel to the scattering plane rather than perpendicular. This behavior is nearly unprecedented in comets. The specific size distribution and composition of dust particles required to produce this effect are highly specialized. Natural comet dust typically encompasses a broad range of sizes and mixed compositions, resulting in positive polarization in most instances. Laboratory experiments can generate negative polarization under carefully controlled particle sizes, generally within the micrometer to submicrometer range, and with specific refractive indices. Encountering these exact conditions within a natural comet coma, where dust is continuously generated and ejected in varying sizes, is extremely improbable. The VLT team estimated this probability to be below 1%. The seventh anomaly is the conspicuous absence of visible outgassing. Richard Kite, Peter Vey, and Avi Loeb analyzed over 4,000 positional measurements from 227 observatories worldwide, spanning from mid-May through late September. They detected no discernible deviation from purely gravitational motion. The residuals in right ascension and declination were consistent with zero. On the surface, this might seem normal, as gravity dictates orbital motion. However, for active comets, this is not the case. When comets outgas, the resulting vapor jets produce recoil forces that subtly deflect the nucleus from its gravitational trajectory. These non-gravitational accelerations are well documented and routinely measured for comets within our solar system. The magnitude of this effect depends on the comet's mass and the intensity of its outgassing. Small, active comets exhibit significant deviations, while larger comets show smaller, yet still detectable, deviations. 3I Atlas is outgassing vigorously, losing approximately 25 kilograms per second, according to Webb observations. This should generate a measurable recoil. The fact that no deviation was detected implies either perfectly symmetrical outgassing, causing the forces to cancel, or that the object's mass is so substantial that the recoil falls below the detection threshold. perfectly symmetrical outgassing contradicts the observed anti-tail and geometric plasma patterns, which indicate a lack of symmetry. Therefore, the object must be exceedingly massive. Working backward from the detection limits, the analysis concluded that 3I Atlas must possess a mass of at least 33 billion tons. This is approximately 1,000 times more massive than 2I Boris, despite being only a few times larger in diameter. The implied density is considerably higher than that of typical comets, which are loosely aggregated rubble piles with significant void space. High density suggests either that the object is primarily rocky rather than icy, or that it possesses an internal structure that is not porous like that of conventional comets. The eighth anomaly revisits the alignment of the WOW signal. A 9-degree directional match with a 6% random probability was observed. While this anomaly is the weakest on its own, representing a significant uncertainty cone in interstellar space, its correlation with the other 7 anomalies adds another layer of statistical improbability, multiplying all 8 probabilities together. 2% for trajectory alignment, 0.005% for planetary encounter timing, below 1% for the mass and velocity combination, below 1% for the nickel-iron ratio, under 5% for the low water composition, below 1% for the extreme polarization, below 1% for the extreme density indicated by the lack of non-gravitational acceleration, and 6% for the WOW signal alignment. The cumulative probability is staggeringly small, measured in parts per quadrillion. Lowe and his colleagues calculated the precise value to be less than 1 in 10 to the 16th power, or 1 in 10 quadrillion. To put this into perspective, observing 10 quadrillion random interstellar objects would yield, by chance alone, approximately 1 with this particular combination of characteristics. However, a statistical pitfall exists here. After an event has occurred, it is possible to make almost anything appear improbable by selectively choosing which characteristics to measure and which probabilities to multiply. This is known as the Texas sharpshooter fallacy, where one shoots bullets into a barn wall and then draws targets around the bullet holes to create the illusion of hitting bullseyes. The counter-argument to this fallacy is to define criteria in advance and apply them consistently. Lowe's team attempted to do this. The 8 anomalies were not cherry-picked after their unusual nature was discovered. Rather, they represent the types of parameters one would naturally examine for any interstellar visitor. Trajectory, mass, composition, and behavior are fundamental observables. The fact that all of these parameters happen to fall at the unusual end of their respective probability distributions is not a matter of selecting convenient facts, but rather an indication that the object itself is consistently anomalous across independent measurements. This is why 3I Atlas ranks at 4 on the scale. It is not a single bizarre characteristic that might be a fluke, but 8 independent characteristics, all pointing towards a low probability scenario. While natural explanations exist for each individual anomaly, explaining all of them simultaneously requires the confluence of multiple rare conditions, which becomes a convoluted natural explanation. The alternative is that 3I Atlas is artificial, a probe, spacecraft, or other technological construct dispatched from another star system to explore our own. If this is the case, all 8 anomalies are readily explained as expected features. The trajectory alignment signifies deliberate navigation. The planetary encounter timing points to mission planning. The extreme mass and velocity are attributable to propulsion system capabilities. The nickel-iron ratio suggests materials engineering. The low water content could represent a thin surface layer designed to mimic cometary activity while protecting underlying systems. The extreme polarization might be a characteristic of its surface coating. The absence of non-gravitational acceleration points to the structural integrity of a solid, manufactured object. The WOW signal alignment indicates the transmission location from 48 years prior during its approach. This hypothesis aligns with 8 predictions. This is how Occam's razor is intended to function. The simplest explanation, meaning the one with the fewest independent assumptions, is preferred. 8 separate unusual natural conditions versus 1 extraordinary artificial origin. The artificial hypothesis is simpler in this regard, despite sounding more extraordinary. However, extraordinary claims demand extraordinary evidence. Statistical anomalies, however improbable, are not equivalent to physical proof. We require observations that cannot be explained naturally, even in principle. This could include radio transmissions, resolved surface structures revealing manufactured features, trajectory changes inconsistent with outgassing or radiation pressure, or the active deployment of secondary objects. Something definitive that resolves the ambiguity. Ranking at 4 signifies uncertainty. It could be natural, or it could be artificial. The data does not compel a conclusion in either direction. If post-perihelion observations reveal continued natural cometary behavior, the ranking would decrease to 2, indicating something unusual but likely natural. Conversely, if observations show impossible natural behavior, controlled maneuvers, or obvious technological signatures, the ranking would escalate towards 10. We are currently in an intermediate state, suspended between mundane and profound explanations. The 8 anomalies unequivocally establish 3I Atlas as noteworthy. Whether it is noteworthy as the most peculiar comet ever observed, or as the first confirmed contact with extraterrestrial technology, hinges on data yet to be acquired. Observations in December are expected to push the ranking in one direction or the other. Until then, rank 4 is its position, a designation signifying genuine uncertainty about what we are observing and underscoring the importance of that uncertainty. The Prophet and the Mothership. Brandon Biggs did not set out to be known as the prophet who foresaw the assassination attempt on Trump. Yet, in April 2024, months before the July 13th shooting at a Pennsylvania rally, Biggs recorded a video detailing a vision. He described witnessing a bullet narrowly miss Donald Trump's ear, coming so close that it ruptured his eardrum. He depicted the ensuing chaos, the bloodshed, and Trump's survival, albeit injured. When the actual attempt occurred in July, matching these specific details with unnerving accuracy, Biggs transitioned from an obscure Christian pastor to an overnight viral sensation. This track record, this single, incredibly specific prediction that materialized, lends a weight to his subsequent visions they might not otherwise possess. When someone foretells something so improbable and so detailed, their subsequent pronouncements gain attention, even from those skeptical of prophetic claims. In a video released in mid-October, Biggs elaborated on his next vision, this one concerning extraterrestrial beings, specifically a colossal mothership arriving on Earth. In this vision, Biggs described an immense alien craft hovering over the Vatican and Mayan ruins in Mexico. He emphasized that it was not multiple ships, but a single entity. When he inquired within the vision whether there were multiple craft, he was told, "No, just one enormous vessel." The ship traversed the ocean slowly, in plain sight, visible to everyone and broadcast globally, instigating widespread panic. Subsequently, smaller craft emerged from the mothership. Biggs characterized them as balls of light, diminutive vessels scattering from the primary craft. The timing of this video's release in mid-October, coinciding with 3I Atlas's approach to perihelion, ignited immediate online speculation. Social media buzzed with theories connecting Biggs's vision to the interstellar object. Online forums filled with discussions comparing his depiction of a mothership releasing smaller probes to Avi Lowe's hypothesis that 3I Atlas might deploy mini spacecraft during its closest approach to the Sun. The parallels are striking. Biggs speaks of a single, large vessel deploying multiple smaller objects. Lowe discusses a mothership scenario wherein 3i Atlas, if artificial, would release mini-probes during its closest pass by the Sun. Biggs had actually alluded to this vision earlier, in July, shortly after 3i Atlas was discovered. He described seeing small ships emanating from a larger craft, balls of light emerging from something massive. At the time, most viewers interpreted this as generic prophetic imagery, the kind of vague apocalyptic scenario common in religious visions. However, the July timing, precisely when 3i Atlas entered public awareness, and the mid-October emphasis, just prior to perihelion, created a narrative arc that conspiracy communities found impossible to disregard. The theological framework Biggs employs is crucial context. He does not present these as benevolent extraterrestrial visitors. Rather, he explicitly labels them as demonic entities, spiritual forces utilizing physical manifestations to mislead humanity. In his interpretation, the mothership and its smaller craft represent satanic deception, part of a larger end-time scenario designed to pave the way for the acceptance of the Antichrist. The beings are not aliens in the science fiction sense. They are fallen angels or demons adopting forms that contemporary secular society would interpret as extraterrestrial. This theological lens does not diminish their intrigue from a phenomenological standpoint. If one strips away the spiritual interpretation and focuses solely on the claimed observations, flying objects, a mothership releasing smaller craft, global visibility, television coverage, one is left with descriptions that could apply to physical phenomena, irrespective of their ultimate nature or origin. Whether these phenomena are interpreted as technology from another star system or as manifestations of spiritual entities becomes a matter of individual worldview. The internet, as it often does, facilitated rapid dissemination. Within hours of Biggs's October video circulating, edited versions emerged, directly linking his statements to 3i Atlas. Some versions incorporated images of the object from the Hubble and James Webb Space Telescopes, while others overlaid orbital diagrams illustrating its trajectory. This synthesis crafted a narrative where a Christian prophet and a Harvard astrophysicist were independently describing the same event through different conceptual frameworks. Lowe discusses orbital maneuvers and mini-probe deployment, while Biggs speaks of motherships and balls of light. Although the vocabulary differs, the core scenario aligns. Mainstream media largely overlooked this connection. Prophetic visions are not conducive material for science journalism. However, alternative media, conspiracy-focused platforms, and religious communities aggressively amplified it. For certain audiences, the combination of Biggs's credibility, bolstered by the Trump prediction, along with the scientific anomalies surrounding 3i Atlas, created a perfect storm of validation. From one perspective, it represented a spiritual warning corroborated by empirical observation. From another, it was interesting astronomical data being framed within an apocalyptic religious interpretation. The detail about balls of light is particularly compelling, as it echoes descriptions found in unidentified aerial phenomena, UAP encounters. Reports from military personnel frequently describe luminous spheres exhibiting movement patterns inconsistent with known aircraft. While these may not be directly connected to 3i Atlas, the descriptive overlap between Biggs's vision and existing UAP reports added another layer of corroboration for those predisposed to see connections. Skeptics argue that prophetic visions are inherently unfalsifiable until they either occur or do not. Biggs can describe any event, and if it fails to materialize, supporters may contend that the timeline was misinterpreted or the prediction was contingent upon human actions. Conversely, if something vaguely matching the description transpires, it is counted as a success, even if the details are imprecise. The Trump assassination prediction stands as an exception, specific and accurate enough that explaining it away requires convoluted rationalizations. However, one accurate prediction does not validate all subsequent claims. Furthermore, the issue of influence must be considered. Biggs has access to the internet, and follows the news. By October, 3I Atlas was a prominent headline. Lowe's mothership hypothesis had already been discussed in major publications. It is conceivable that Biggs consciously or unconsciously absorbed this information and integrated it into his religious framework. The distinction between vision and imagination can be blurred, especially when both draw from the same informational environment. Claiming divine revelation about something one has read, even without conscious recollection, is a well-documented psychological phenomenon. However, the July mention complicates this. Biggs described ships and balls of light back when 3I Atlas was known only to a limited circle of specialists. Lowe had not yet published detailed papers on the technological hypothesis, and the mothership scenario was not a mainstream topic of discussion. If Biggs was unconsciously drawing from media coverage, what information was available in early July that could have planted these specific images? The object had only just been discovered, and initial reports described it as a comet. Interesting for its interstellar origin, but not yet burdened with discussions of anomalies or technological speculation. This timing issue is why some give Biggs's claims more credence than they might otherwise. Either he was extraordinarily lucky in predicting that an interstellar object would become associated with mothership theories, or he possessed genuine insight through whatever process generates his visions, be it psychological, spiritual, or otherwise. The Trump prediction makes the lucky guessing explanation more difficult to accept. From a sociological perspective, Biggs represents something significant. Irrespective of the accuracy of his prophetic claims, he serves as a conduit through which scientific uncertainties are translated into religious narratives. 3I Atlas, with its statistical anomalies and technological hypothesis, creates fertile ground for apocalyptic interpretations. Individuals seeking signs of the end times perceive a mysterious object from the stars, potentially deploying probes into our solar system, as precisely the kind of event that would precede major prophetic fulfillments. Concepts such as the beast system, a one-world government, and the revelation of hidden truths, all classic eschatological themes, find resonance in interstellar visitor scenarios. This phenomenon is not new. Throughout history, every major astronomical event has been interpreted within religious frameworks. Comets were once viewed as omens, eclipses as indicators of divine displeasure. Modern UFO phenomena have been assimilated into both secular and religious explanatory systems. 3I Atlas is simply the latest celestial occurrence being incorporated into these interpretive structures, amplified by social media and the genuine scientific puzzles it presents. What makes this case particularly unusual is the convergence of factors. We have a prophet with demonstrable credibility stemming from a recent, specific prediction. We have a scientific hypothesis from a respected astrophysicist employing mothership terminology. There is a temporal synchronicity where the vision's details align with a perihelion window when deployment would theoretically occur. And we have an object that is genuinely anomalous to the extent that even skeptical scientists acknowledge its need for serious investigation. This confluence of events offers no definitive proof of prescience, extraterrestrial visitation, or divine intervention. It simply illustrates that when reality presents sufficiently perplexing circumstances, various interpretive systems tend to converge on the same phenomena. Scientists might attribute it to the deployment of probes, while religious figures could interpret it as a manifestation of demonic forces. Both perspectives could be entirely inaccurate, or perhaps partially correct in ways that do not inherently conflict. The technology of a highly advanced civilization would naturally appear miraculous to less developed observers, echoing Arthur C. Clarke's famous assertion that sufficiently advanced technology is indistinguishable from the supernatural. If the celestial body known as 3 Atlas were to release objects, specifically during its perihelion passage, and we observed secondary craft emanating from the primary body, how would different communities process such an event? Scientific observers would meticulously analyze trajectories, spectrometry, and propulsion signatures, seeking to ascertain the origin, purpose, and capabilities of these objects. Conversely, religious communities would likely perceive this as a fulfillment of prophecy, evidence of spiritual conflict, or a harbinger of the end times. Each interpretation would remain logically consistent within its respective framework, and both would feel vindicated by the observed events. This is precisely where epistemology, the study of how we acquire knowledge, becomes critically important. Science grounds itself in observation, measurement, and reproducibility. Religion, on the other hand, relies on revelation, sacred texts, and spiritual insight. When both systems interpret the same occurrence and declare that something momentous is unfolding, yet articulate it through conflicting vocabularies, achieving a resolution becomes exceedingly challenging. One cannot definitively disprove the notion that spiritual entities are utilizing physical craft for their manifestations, nor can one prove that advanced extraterrestrials are not being mistaken for angels or demons. The fundamental frameworks are incommensurable in significant aspects. Nevertheless, we can acknowledge that Biggs described a scenario using terminology derived from his religious background that bears a substantial resemblance to scenarios articulated by scientists employing secular language. Whether this overlap stems from a shared underlying reality, from reciprocal influence and informational cross-contamination, or from mere coincidence, its sociological impact remains undeniable. Millions of individuals, spanning both religious and secular demographics, are now observing 3 Atlas with heightened anticipation, expecting a dramatic unfolding of events. This collective expectation carries significant weight. Should nothing extraordinary occur, and the object simply complete its perihelion passage and continue on a purely gravitational path exhibiting typical cometary behavior, both groups would experience a sense of anticlimax. Scientists who had entertained the possibility of a technological hypothesis would revert to conventional explanations. Religious communities would either adjust their prophetic timelines or reframe their visions as symbolic rather than literal. Life would proceed as usual. However, if something remarkable does transpire, if we witness deployments, intricate maneuvers, or transmissions that scientifically confirm the mothership hypothesis, the religious interpretation would acquire immense cultural influence. Biggs would then be credited with accurately predicting not one, but 2 highly improbable events: the assassination of Trump and the arrival of extraterrestrials. Such a track record would elevate him to the status of one of the most credible prophetic voices in contemporary history. Regardless of whether one accepts his theological framework, the accuracy of his information regarding future events would be difficult to dismiss. The observations scheduled for December will serve as a direct test of these possibilities. If numerous probes detach from 3 Atlas and commence independent trajectories toward Earth or other celestial bodies, this will become evident within a matter of days. Telescopes across the globe are poised to capture these events. The Interstellar Warning Network (IWWN) campaign is specifically designed to detect precisely this kind of signature. We are not entering December unprepared. Rather, we are embarking on the most extensive monitoring initiative ever undertaken for an interstellar visitor. Biggs's narrative adds a layer of human drama and spiritual significance to this scientific observation. Whether his interpretation proves accurate or not, he has ensured that when 3 Atlas emerges from the sun's glare and astronomers release their findings, those findings will be simultaneously filtered through a multitude of interpretive lenses. The narrative transcends mere scientific inquiry, becoming cultural, spiritual, and existential. This broader engagement may, in fact, be entirely fitting. If we are witnessing something that fundamentally challenges our understanding of our place within the cosmos, whether through technological contact or other means, it ought to resonate beyond our scientific institutions. It should engage our spiritual traditions, our philosophical constructs, and our deepest inquiries into meaning and purpose. 3 Atlas has become a crucial litmus test for humanity's diverse methods of comprehending the unknown. What we perceive in this event reveals as much about ourselves as it does about the object itself.